Alrighty, everybody, how we doing? It's your boy, it's Joe, coming back, live in the flesh, coming in 36 colors and on 56 stations across 121 countries. I have no idea if that was right, but here I am. Hope everyone's having a good day. I'm having a beautiful day, guys. Hold on one second. Gotta make sure everything. Make sure everything is looking good. All right. Everything looks good. All right. Before I start today, I need to give a big shout out to somebody today. What's up, Paul? Yo, Paul, thank you for the follow, my brother. How we doing, man? Thank you for joining me tonight, my brother. I appreciate that, brother. All right. Like I said, before I start off the show today, I need to give a big shout out to somebody today. All right. You know, it's been a tough year. It's been a tough year for me. It's been a tough year for everybody. You know what I'm saying? But this year, though, you know, losing my job, getting injured, kind of really put my whole life on the back, set me back a heck of a lot. And you know, I got to give a big shout out to my big sister. She's 100% always got my back. So if you're out there, big sis, I'm giving you a big shout out. I love you so much. All right, thank you very much, big sister. Mwah. I love you with all my heart. All right, I had to do that just to start things off, guys. I tell you what, she's been an angel to me. She's been a 110% in support always of whatever I do. And she's always been there for my kids, you know, and everybody else. So I love you, big sis. Remember that. All right. All right. Good, man. Good to hear, Paul. Yeah, man. You know, this stream's been going real good, brother. I don't know if you've caught any of the streams in the past or have caught any of the content prior. So what this stream is about is we're gonna be diving into it's called the CCNA certification, and that is the Cisco Certified Network Associate exam. And what that is it's fundamental network knowledge when you're dealing with network devices like switches, routers, hubs, bridges, how to set all that, how to set and configure those types of devices for you know, network connectivity, for campuses, for enterprises, you know, for your own house. You know, this exam right here is like a gateway exam to like junior level IT positions and stuff like that. And what this stream is going to be about is this stream is a journey from my beginnings into this type of career to you guys are going to be witness to when I actually get this actual certification myself. And what my hope is by sharing all this with you guys is not only do you guys get, you know, possibly interested in this certification, you know, but if you guys are looking for a career change, that maybe this might be a career that you guys might have some interest in. So my boy Paul, if you're interested, man, follow this. I'm giving out really good information. I walk step by step what you really need to do to fundamentally start understanding these key topics in this knowledge. So yeah, man, thank you for joining me tonight, brother. So tonight, what we're going to do is we're going to be diving into chapter 9. All right, but like we start always every stream, we're going to do a review of what we did yesterday. And yesterday we covered chapter 8. And let me just get my handy dandy book out. And yesterday we covered implementing Ethernet virtual LAN. So it was the start of our discussion about VLANs and what VLANs represent. And that's going to be expanded upon as we get into tonight's topic, which is STP, which is Span and Tree Protocol. All right, Span and Tree Protocol. We're gonna dive into it, but just to give you a quick overview, Span and Tree Protocol is a algorithm that is used inside of these switches. So when you create redundant links across multiple switches, you don't create what is called a broadcast storm. What a broadcast storm is when you send out a broadcast or an or a unicast frame through your network, and if you don't have STP or rapid STP being used inside of those switches, what will happen is that frame will be continuously continues to be broadcast and flood your whole entire network up, making your switches unusable, making your network unusable, and making your PCs, your network devices, all of that stuff will be unusable, because what will keep happening is that frame will keep on being flooded to all those devices. And that will cause, interruptions in service, that will cause bad service, and at the end of it, you'll just have no service at all. So that's where we're gonna be taking our a hard look at today. That's gonna be all of chapter 9. It's STP, and then it's going to then at the very end of the chapter talk about some of the differences between STP and Rsdp. Rsdp is just a upgraded version of STP. But to take the step back again, we're gonna do a quick review on the Pearson's test prep program. We're gonna do the review on implementing Ethernet LANs, all right, VLANs. And just to give an overview, if you didn't join us yesterday, VLANs are LANs inside of your switch. So if you have your switch with the multiple ports or interfaces, what you're doing is you could break off sections or individual ports or interfaces off in their own VLAN, off in their own LAN. So you can break a single or multiple interfaces or ports into their own actual LAN. So they can have their own unique local area network, their own broadcast network. All right. So, so that's what we're going to be diving into today. I got Cisco Packet Tracer up already. We're going to be using Cisco Packet Tracer, all right, today, so we can go over Span and Tree Protocol. Just because I don't want to blow up my computer using Cisco Modern Lab tonight. Paul, anybody joins me, if you've got any questions, please ask me questions as we go along. That's what this is all about. I want you guys to get as much knowledge out of this as possible, because not only is this for me to advance my understanding of this, I want you guys to be able to understand what we're going over. That way, again, if I can spike some interest in you to start thinking about these topics, maybe this might be a career choice for you. So I hope you can stick around for a while. Got yourself some coffee. Big bug time. Coffee. All right. Let's get to it. Let's get to the business. All right. Enough of that. All right. Let's go over to the big screen. Honeydew. Whoop, whoop. Gotta love that honeydew. All right. Turn my thingy around so I can see. Let me get my markers ready. All right. Clear my board real quick. let's take a dive into spanning tree protocol, everybody. Where's my mouse? There's my mouse. All right. Let's go to the practice. Let's get some practice up in here. All right. All right. So we'll do the full exam just to kind of beat us up a little bit. Make sure we have this knowledge really built into our heads. Let's go down to chapter 8. Implementing Ethernet virtual LANs. All right. Let's jump into the test here. All right. Which Cisco iOS command can you use to display which VLANs are supported over a specific configured switch trunk? So this was catching me yesterday. So I believe it is show interface switch port trunk. Show interface switch port trunk. I believe it's this one. Let's see. Oh, I was wrong. All right, so it's the show interface trunk. All right. So both the show interface trunk and the show interface switch port command will display the VLANs that are allowed over the trunk. Okay. So let's kind of put that into our memory. Show interface trunk. It's not show switch port trunk. All right. Let's go to the next one. How many questions do we only have 5? So we'll have to redo this one afterwards. That's fine. All right. Based on the figure, what Cisco iOS command would be used on switch SW4 to correctly configure switch 501 to be used as an access port in VLAN 30? All right. So we want to use this as an access port. All right. Based on the figure, what Cisco iOS command would be used on SW4 to correctly, all right. So that'd be switch port access VLAN. VLAN, yep, switch port access VLAN 30. So we would already had put the switch port mode access in. And then we go behind and then we put switch port access VLAN and then whatever number after that. You know what I need to pull up? Let me get my markers up real quick. Need my markers. Let me just make sure my markers are working already. Yep, they're working. All right. What is true about the command switch port non-negotiate? If connected to a switch that uses dynamic desirable, the neighboring switch will not trunk. Maybe this is only by default. Nope. This command prevents a switch from being a trunk port. It is used on routers to prevent VLAN hopping. This will cause DDP messages to be sent, preventing trunks to being non-negotiated. If connected to a switch that uses dynamic desirable, the neighboring switch will not trunk. Let's go with 1. I have a feeling I might get this one wrong. Oh, we got it right. All right. Refer to the exhibit and diagram to make it possible for all traffic to pass between PC1 and the local area network and PC2's local area network. The link between SW1 and SW2 will be configured as a trunk. So what they're saying is this one right here will be configured as a trunk, okay? Which Cisco iOS command could be used on switch SW1 gigabit 0-1 interface to force it to actively attempt to trunk with SW2. So what do we want to do? So we got the switch port mode, dynamic desirable, switch port mode, dynamic auto. Switch port dynamic auto is passive, so we don't want that. Switch port trunk negotiate, switch port trunk auto. So let's go with switch port mode dynamic desirable, because by default on gigabit 0-1 on SS2's switches interface, it's probably by defaulted on the dynamic auto by default. So if we switch S1's gigabit to dynamic desirable, that should make a trunk. Let's check it out. All right, we were good. All right. In this network, all switches are powered on, and all relevant VLANs have been configured correctly and are working. Based on the output in the exhibit, which of the following statements is true about SW2? So SW2. So here, this is SW2 right here. All right. And what do we got? What do we got? Based on the output. So let's look at the output real quick. So here we go. Here's our configuration right here. Let's take a look. So S2 show VLAN brief. So pretty much all of its ports are residing in the default VLAN 1. It has multiple VLANs made. So it has multiple VLANs. It has VLAN 5 that's coded as named sales. VLAN 10, 11, 12, 13, 14, 15, 16. So it has all VLANs. It has an array of VLANs, but it has no actual ports assigned to any of those VLANs. But they're all active. They're all made. They all have names. So let's check out what we got. 3 interfaces are trunking. Let me see. I don't think it gave any information. This is just the show version. I don't care. And it's just the showing the VLAN. So I don't know if anything is trunked. All right. Only 1 interface is trunked. 2 interfaces. Not enough information is provided to know which interfaces are trunking. So pretty much it's not giving us enough information, at least in my opinion. Let's see. All right. 3 interfaces are trunking. So let's take a look at that again. It's saying 5.0. But where is it stating that? I gotta see now. Ah, okay, I see what I might have missed. What's up, bud?
Can you have red note?
Can
you have red note?
There's no more.
There's a little.
It's a set left.
Yeah.
All right, yeah. So I'm trying to see where. So Cisco's processor revision with last reset with powered on. 1 virtual Ethernet interface, 24 interfaces, 2 gigabits, password recovery. Show VLAN brief. I'm just trying to see where it's stating that information. Oh, I don't know. So let's see. The show version command states that into the show VLAN brief. Oh, I guess so this is like a trick question, because since it's not showing 5.0, so it's right here. So since it's not showing 5.0.22, 5.0.23, and 5.0.24, and that's where it's getting us right here. So I get it now. All right, trick question. So it states that there's 24 fast Ethernet interfaces. Okay, cool. We come down here and we see that we have 501, 2, 3, 4, 5, all the way to 21. And it's not showing 5022, 5023, and 5024. So what this question is implying that the show VLAN brief will not show trunking ports. Okay. All right. I'll take that. I'll take that hit. I'll take that L. All right. All right. We did pretty bad on that. So let's do another exam. All right. Let's hopefully it gives us some different questions on this one. It might actually give us the same. I hate when it gives us the same because I need to nail this into my head. All right. Randomize questions. Yes. Randomize. Oh, randomize. I want random. Random, random, random. All right. Start it again. What is true about the switch port? What is true about the command switch port non-negotiate? If the command is used, it will not trunk. The command. All right, man. It gave us the same ones all over again. I hate when it does that. I don't like when it gives us the same ones all over again. All right. All right. I got to figure out a way to randomize those questions a little bit more. Because I don't like that the fact that it gave us all the same ones again. But that's neither here or there. Let's drink some more coffee. All right. Now, let's get into spanning tree protocol, guys. This is going to be a fun one. Spanning tree protocol, very, very important. Very important to how switches work and everything else. We're going to learn a lot about that tonight. So, Chapter 9, Spanning Tree Protocol Concepts. What we're going to be reviewing, configure and verify Layer 2, Layer 3 Ethernet channels, LACP. Describe the need for basic operations of rapid PVST, Spanning Tree Protocol, and identifying basic operations. Root port, root bridge, secondary, primary, and other port names, port states, forwarding, blocking, port fast benefits. All right. Here's a quick overview of what the chapter is going to be going over. Spanning Tree Protocol, STP, allows Ethernet LANs to have added benefit of installing redundant links in a local area network. Okay, while overcoming the known problems that occur when adding those extra links. Using redundant links in a local area network design allows the LAN to keep working even if a link fails. So the reason why we're going to be adding redundant links, redundancy is the act of taking a secondary, a third, or a fourth measure, in the occurrence of a failure, this can go with anything. This can go with planes, cars, trains, mechanically wise, anything. Usually there's some kind of redundancy built into something mechanically wise. That way, if something was to fail, there's a redundant system in place so that the system can continue to operate, either at full capacity or at least at half capacity. So the redundancy, the reason why we want to build in redundancy into our networks, into our links, is say if we were to have an interface fail on our switch per se, what would happen is Spanning Tree Protocol would see that link failure, and then it would activate. It would turn a blocking port into now a forwarding port, so that the network can continue to forward forward frames throughout its network. So that's the reason that's the reason for redundancy. Now, when we build redundancy into our networks, though, what will happen if we don't have Stp? That will be the case where we will create a broadcast storm. And I'll give a quick illustration of what a broadcast storm may look like. So we're going to say we have our switch 1. All right, we'll have another switch here. We'll say switch 2. All right, and we'll take another switch here, switch 3. All right, we're going to be building redundancy inside of our network. So we're going to have a link here. We're going to add that link to switch 3. We're going to add another link to switch 2. Then we're going to take another link and we'll add it back to switch 1. What we've built is some kind of redundancy inside of our network, okay? Now, if we didn't have Stp, all right, spanning tree protocol, if we didn't have spanning tree protocol working inside of our network, what would happen is if we were to send a frame out of S1 to S3, all right, a broadcast or a unicast, okay, that FFF, all right, if we were to send that broadcast frame through our network, it would go to S3. S3 would forward it to S2. S2 would forward it to S1 now, all right, but you got to think at the same time it's forwarding in this direction, it's also going to be flooding and forwarding out the other direction. So at the same time this frame is going around in circles this way, that frame is still, that frame is then going around in this and going back in this direction as well. All these, so you would have a situation where you would have one frame going around this loop in an indefinite time period. It would continue to go around and around in both directions indefinitely, it would eventually cause failure, and then it also prevents any other traffic going in and out of this network to get to any kind of destinations. You would at this point have a complete network failure at this point, all right? And that is called a broadcast storm, all right? So Stp prevents broadcast storms, all right? All right. Let's continue on here, all right? Historically, the IEEE first standardized Stp as part of the IEEE 802.1d standard back in 1990, with pre-standard versions working even before that time. Over time, the IEEE improved Stp with the eventual replacement of Stp with an improved protocol, and that is Rsdp, or Rapid Spanning Tree Protocol, all right? The IEEE first released Rsdp as an amendment in the 802.1W in 2004, integrating Rsdp into the, and now it's integrated, first it added it to the amendment, so that was the 802.1W, all right? That was the amendment to the 802.1 Delta, but then it integrated Rsdp into the official IEEE standard back into the 802.1 Delta. Okay, so now Rapid Rsdp is now integrated into the IEEE standard, the 802.1 Delta. All right. An agreement could be made to ignore Stp today and instead focus solely on Rsdp. Mostly modern networks use Rsdp instead of Stp. The most recent model of iOS version Cisco switches default to Rsdp instead of Stp. Plus, the CCNA 200-301 exam topics mention Rsdp by name, but not Stp. So, even though this chapter is going to be solely covering the Stp, the spanning tree protocol, the actual exam itself doesn't mention, it states right here, the exam itself is not going to mention Stp by name, but instead it's going to mention Rsdp. What the chapter, though, is going to attempt to do, it is because of the fundamental knowledge that we need to gain from here, and because Stp was the originator, it is going to take that step back so we can first understand what STP is. Then it's going to introduce us to Rsdp. Okay. However, Stp and Rstp share many of the same mechanisms, and Rsdp improvements can be best understood in comparison, all right, in comparison to Stp. For that reason, this chapter presents some details that apply only to Stp as a learning tool to help us better understand as we continue what Rsdp is going to be. Okay. This chapter is organizing the material into 3 sections. All right. The first section presents some core concepts about Stp and Rstp. Discover a tree made of nodes, switches, okay, and links. So no loops exist in that network. So again, Stp, Rstp prevents those loops from happening by blocking. In the simplest terms, it's going to block one of those ports, all right? Instead of all the ports forwarding that frame, it's going to select the port to block, all right? That way, it stops that loop from ever happening, okay? All right. The second section of the takes a brief look at the area of which Stp differs from Rsdp, all right, and how Stp reacts to changes in the network. This chapter ends on the third major section that details Rsdp, including how Rsdp works much better than Stp when reacting to changes. Okay, so obviously they made some improvements to the Stp itself, to the algorithm itself. Created Rsdp, Rapid Tree Protocol. Coffee time. Woo! All right. Now we're gonna take the Do I Know This Already quiz. This is an overview of the chapter before we actually get into the chapter. Okay, so this is going to allow us that moment to see how much knowledge we actually have about this chapter prior for us taking the deep dive into it. Okay, I love to take this just so I can say, I can take this step and say, what do I already know about Stp? Or as we continue on to these chapters, as we continue on, guys, you're gonna start seeing that as we get deeper and deeper and deeper into these topics, I'm gonna start really, really struggling to answer these questions. But luckily enough, I've spent some time though, looking at some of these major topics in this books like Stp, and some of the prior topics that we've already covered. Okay. All right. Which of the following port states are stable statuses used when Stp has completed convergence? So, convergence. We can think of convergence as when it has completed its initiation process. So, when Stp has completed its complete process of how it's already figured out what to block, what ports to keep open, to keep forwarding. That's what the word convergence is meaning. Okay, so we don't get hung up on just this one term right here. All right, that term kind of messed me up in the beginning. So we have to select 2 answers. So let's go over here. Let me get my handy dandy and let's make that a little bit bigger. All right. So we got blocking, forwarding, listen, learning, and disregarding. So it's completed its initiation. It's already decided. It's already listened and learned all the ports. It already listened and learned for all the hello BDUs and whatnot. It's gotten all that information and it's made its complete decision. Now, what is it doing? Now it's in the state of blocking and forwarding. So we're going to say A and B for number 1. All right. Let's go down. Which of the following bridge IDs win elections? Which of the following bridge IDs win elections as root, assuming that the switches with these bridge IDs are in the same network. So when a switch for a switch to choose, for Stp to choose an actual root bridge, it goes through a process of looking at these BDU messages and getting the the bridge ID numbers, and then after it looks at the bridge ID numbers, it takes a look at the MAC addresses. All right, the MAC addresses of these switches, these bridges. Okay, and what it's looking for is the lowest numeral, the lowest MAC address number. Whatever has the lowest MAC address number is the bridge, is going to be the switch that's going to win that election and become the root, the actual root switch, the root bridge. Okay. All right, so we got 32.769, 32.769. All right, so automatically we can kick these guys out. All right, so now we have 4097, 4097, and then we have 4090, 4961. So 49. So automatically it's going to be between these two right now, and obviously it's going to be C. So let's go with C. See how we did. Get my thingy up. Let's go with C. All right. Which of the following are transitory port states used only during the process of Stp convergence? All right. Which of the following are transitory port states used only during the process of Stp convergence? So what it's saying is what are the port states? What are the ports doing? So so when it's as it's doing its initiation. So we got to take that step back from that first question now. So when it's doing that initiation, when it's getting those hello BDUs and whatnot, what state are those ports in? All right, so that's what that transitory port state is asking. So in the beginning, as it's now going through the actual process, it hasn't completed its process. It's going through that process. What is the state those ports are in? So those states are listening. All right, they're listening for those BDUs, and then they're learning the bridge IDs. It's learning which port. Which bridge port to choose, which interfaces it's going to then block and forward. So it's going to be listening and learning. Okay. Let's go with 3, and we're going to say C and D. All right. Let's go here. Which of the following facts determines how often a non-root bridge or switch sends the Stp hello BPDU messages? Okay, which of the following facts determine how often a non-root bridge or switch sends its Stp hello PPDUs? So that's those PPDUs. That's what I keep saying. It's going to be sending those hello messages. Okay, now that is set. That timer is set by the root bridge. All right, the root bridge. So the hello timer as configured on the switch. Nope. The hello timer as configured on the root switch. So it's configured by the root switch. Let's just ask the other last two. It always is that. Nope. It could be, but that's all depends on the root bridge. The switch reacts to the PPDUs received from the root bridge by sending another PPDU 2 seconds. No, it's only so it's the hello timer as configured on the root bridge, the root switch. So we're going to say 4, we're going to say B. All right. Which of the following Rsdp port states have the same name and purpose as a port state in the traditional Stp? Which of the following Stp port states have the same name and purpose as a port state in traditional Stp? So I'm going to say blocking, I'm gonna say blocking and learning. I'm shooting from the hip on this one, but I think I'm close on this one. Shooting from the hip. So I'm gonna say A and D, blocking and learning. Shoot from the hip. All right. Whoa. All right. Rsdp adds features beyond Stp that enables ports to be used for a role in another Rsdp adds features beyond Stp that enables ports to be used for a role in another port at the same on the same switch fails. Rsdp adds features beyond Stp that enables ports to be used for a role if another port on that same switch fails. Okay, which of the following statements correctly describe a port role that is waiting to take over for another port? Okay, so which of the following statements correctly describes a port role that is waiting to take over for another port? So we have an alternate port that waits to become root port. We have a backup port that waits to become root port. We have an alternate port that waits to become designated port. We have a backup port that waits to become designated port. So what do we got here? So we got a couple of terms. We have alternate and we have backup. And then we have root and then we have designated, okay? So an alternate port waits to become root. And then a backup waits to become designated. Let's go with A and D on this one as well. Again, I'm shooting from the hip on this one, guys. Shooting from the hip. Ba-bow. Ba-bow. All right. All right. With Stp features, what Stp features cause an interface to be placed in the forwarding state as soon as an interface is physically active? What Stp features causes an interface to be placed in the forwarding state as soon as an interface is physically active? All right. Now that is port fast. Okay, port fast is what does that. Okay, so we're gonna say 7. 7 is D. All right. Let's check our answers, guys. I hope we did all right. I think we might have got one wrong. All right. So we got A and B on number 1. We're good. We got C. We got CD. We got B. We got one wrong. We got one wrong. This is B. All right. 6, A and D, and then 7. All right, so let's take a look back on 5 to see what we got wrong. And then let me just mark this. We should have put B. All right, let's take a look back on 5. Which of the following Rsdp ports state have the same name and purpose as a port in the traditional Stp? So it's saying B and D, so forwarding and learning. All right, so I was wrong. So it's forwarding and learning. Cool. All right. So that's so. We have at least some fundamental knowledge about what we're going to be getting into. Okay, that's all this do I know this already quiz is determining. It is trying to make us it's giving us the ability to say, do we really know everything about this chapter so we don't have to waste our time? Obviously, we don't know everything. Okay, I don't know everything, so that means let's take a deep dive into this now. Okay. All right. Let me wet my whistle. Let me wet my whistle. All right. Let's clear the board. And let's take the deep dive, everybody. Take the deep dive. All right. I know you guys love my singing voice. It's beautiful. All right. Without some mechanisms like Stp, span tree protocol, and rapid Stp in a local area network with redundant links would cause Ethernet frames to loop indefinitely. All right. With Stp or Rsdp, some switches block ports so that these ports do not forward frame. Stp and Rsdp intelligently chooses which ports to block with 2 goals in mind. All devices in the VLAN can send frames to all other devices. In other words, Stp and Rsdp does not block too many ports, cutting off some part of the local area network from parts. So what it's stating is, even though it's going to be blocking some ports, it's not going to cause the LAN, the local area network, to not be able to forward the frames where it needs to go. So it's it has intelligence. It's an intelligent algorithm that knows that it can't shut down everything to prevent that loop. It needs to leave ports open so the network can still forward frames. Okay. All right. Frames have a short life and do not loop around the network indefinitely. Yep. All right. We knew that. We discussed that a couple times. All right. Stp and Rsdp strike a balance, allowing frames to be delivered to each device without causing problems that occur when frames loop through the network over and over and over and over again. Okay. All right. So this note, the first major, yep. Okay. So it's just stating that as this chapter is going to continue, it's just going to refer to Stp and Rsdp as a combined thing just for now until we get to the part where it's going to separate that terminology. Okay. All right. So Stp prevents loops by adding an additional check to each interface before a switch uses it to send or receive user traffic. If the port is in Stp forward in state in that VLAN, use it as normal. If that if it's in the Stp blocking state, however, block all user traffic and do not send or receive user traffic on that VLAN. So it's stating, all right. Again, let's make our switches. All right. All right. If it's in the forwarding mode, it's going to forward traffic still, okay? But if it's in the blocking mode, all right, it's not going to forward that traffic, okay? Traffic's not going to flow out of that link at all now, okay? So any traffic that has to go, say here, it has to take this adventure, all right? But we're going to get into how it chooses. There's a math that it's going to do to choose which ports are best to block and which ports are best to forward out of. There's going to be a math that we're going to have to do to figure out how it all does that, all right? All right. Note that Stp states do not change the other information that you already know about switch interfaces. The interface states of connect, not connect, does not change. The interfaces optionally state as either an access or trunk port does not change. All right, so it's not gonna reconfigure your interfaces. All right, it's not gonna change that information. It's not gonna change a trunk port to an access port. It's not gonna disconnect or it's not gonna change those states. All right. It's just blocking. It's just gonna make one port blocking and one port forwarding. Okay, that's all it's doing. All right. Stp adds an additional state with the blocking state, basically disabling the interface. It just adds that additional state to your interfaces. Okay. In many ways, those last two paragraphs sum up Stp. However, the details of how Stp does its work takes a fair amount of study and practice. The first major section of this chapter begins with explaining the need for Stp and the basic ideas of what Stp does to solve the problems of looping frames. The majority of this section then looks how Stp Rstp goes about choosing the switch ports to blocks to accomplish this goal. Okay. The need for spanning tree protocol. Stp prevents three common problems in an Ethernet LAN. All three problems occur as a side effect of one fact. Without Stp, some Ethernet frames would loop around the network for a long time, days, pretty much forever, until somebody either shuts down that switch or disconnects an interface. That frame will continue looping. Just one looping frame causes what is called a broadcast storm. There's that term, broadcast storm. Broadcast storms happen when any kind of Ethernet frame, broadcast, multicast, or unknown unicast frames loops around the local area network indefinitely. Broadcast storms can saturate all links with copies of that one single frame, crowding out good frames as well as significantly impacting end user devices, performance, and making the PCs process. So it's pretty much stating that if you have a broadcast storm, what's going to happen is those frames are going to be still processed by every single one of these end user devices. So end user devices, these PCs, all right? Not only is it going to be going around your whole network, all right? So this is illustrating how it's going to be continuously going around that network, and it's going to be going around in multiple directions. So it's going to be even going back this way, all right? And those frames will be repeatedly bombarding your end user devices. It's going to be continuously bombarding your switches. You're going to be ending up with a complete cluster, a cluster mess of just frames that are just infinitely just going, all right? And your CPU, it's going to continue to demand, you know, additional resources on everything, all right? That's why this is very important. All right. Remember that LAN switches, the logic tells switches to flood, broadcast out all interfaces, okay? So to get back to the fundamentals of what switch logic does, all right? So that goes back to a couple chapters ago when we first started talking about switch logic. When a switch gets a broadcast frame, what does it do? It floods that frame out of all its interfaces, out of all its ports, all right? It says, okay, I got a new broadcast here from the FFF, all right? I'm going to send this out to everybody so everybody gets this message in my LAN, okay, in my local area network, so everybody else can get a copy of this message, all right? So everybody else can get one. That is what is causing all of that, you know, madness. Is they had to think of something that corresponded with the switch's already logic, because we don't want to mess with that logic. That logic helps us, okay? That flooding that the switch does is a crucial part of what a switch is. We needed to continue to do that, but we needed to create something that when we add that redundancy to that network, that it doesn't, that logic doesn't destroy our network, okay? All right, let's keep it moving. All right, the storm also causes much more subtle problems called MAC table instability. So this is a big one, MAC table instability. All right, let me highlight that. MAC table instability. Okay, that's a good one right there for us to just take a deep mind look into. So going back to switch logic now. All right, to switch logic. All right, when that frame comes into the switch, all right, what is that switch going to do? All right, that switch is going to add that MAC address, all right, that source. It's going to add that source MAC address to its MAC table, all right, MAC address table. MAC address table. All right, so when that frame comes in, choo-choo, it's going to say, okay, here's the source MAC address, all right, and then it's going to send it out. It's going to take a look at the destination. Again, this is a broadcast, so it's going to flood it out, all right? But in that broadcast storm, what's going to happen is that same frame, though, is now it's going to come back in this direction, choo-choo, all right? And what it's going to be, it could pick up a different source MAC. So then it's going to say, oh, man, now, well, it's going to have that same, let me take that step back. It's going to have that same source MAC address, but it's going to be coming into a different interface now. It's going to be coming out of this interface. So instead of it saying, okay, gigabit 0-1 has the 1111111 MAC address, all right? Now what's going to happen is that same frame, that 11111, it's going to come in through its gigabit 0-1, that 111111. Now it's going to say, okay, hold on. Now 111 is out of my gigabit 0-1. It's not out of my gigabit 0-0. So it's going to add now that that same source MAC to that gigabit 0-1, even though it originated from the gigabit 0-0. All right. So again, this is what it's called: MAC table instability. MAC table instability. All right. That's what's happening. Is it's going to get that frame. All right. Then it's going to process it. It's going to flood it out, but it's going to come back now through a different interface, and it's going to say, okay, that source is coming out of this now instead of this. So it's going to destroy your MAC address tables. All right. All right. Let's keep it moving. All right. The looping frame in a broadcast storm also causes a third problem. Multiple copies of the frames arrives at the destination. Consider. All right, we covered that. All right. So broadcast storm, MAC address, table instability, multiple frame transmission. Side effect of looping frames in which multiple copies of that frame are delivered to the intended host, confusing the host. So that is what it's. So that is the fact of that frame. That frame going to Bob. All right, you sent that frame to Bob's. Bob's in it. You know, Bob's the PC. What's going to happen is that frame again is going to come. It's going to come again. 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 Bob's PC is going to be overloaded with that same frame over and over and over and over again. All right, it's just going to be adding more stress, and it's going to be eating up more resources on that host. Okay. All right. Again, this whole thing it creates a bad juju. Bad juju. All right. All right, what Stp does. Stp prevents loops by placing each switch port in either the forwarding or the blocking state. Interfaces in the forwarding state act as normal, all right? There's nothing different. It's going to continue to forward those frames. It's going to flood those frames just like it would. That switch logic is not going to change, okay? All right? Forwarding and receiving frames. However, the interface in the blocking state does not process any frames except Stp messages and some overhead messages. So those blocking ports are not going to be forwarding and receiving frames. Still going to be receiving though those Stp messages, the hello messages and whatnot, and that is because that's the redundancy. If your gigabit 0-1 If gigabit 0-1 on your switch, so gigabit 0-1, and you got gigabit 0-2 over here, if 0-1 was in the forwarding state, all right, forwarding state, all right, and gigabit 0-2 was in the blocking state, all right, gigabit 0-1, it's going to continue to forward and receive those the frames as normal frames, all right. Gigabit 0-2 though, it's blocking those frames. Those frames can't get in, all right, and nothing can go back out of it either. But it's receiving those hello messages there. That is because it needs to be receiving those messages. That's it because if, say, gigabit 0-1 were to fail now, all right, gigabit 0-2 needs to come up, and now it's going to be in the forwarding state, all right. Now it is responsible for forwarding and receiving messages, frames within that network now, okay. Now gigabit 0-1, it doesn't even care because now it's cooked, all right. It's burnt out. It's done for, all right. Now gigabit 0-2. He's the superstar, all right? He's in it to win it. He has now turned into the forwarding. He's in the forwarding state now, okay? All right? All right, let's keep it moving. All right. What Stp does, blocks ports to prevent loops. Yep. We've nailed that pretty well. All right. Note, the term Sdp Convergence refers to the process. So here we go. Here's that terminology. The term Sdp Convergence refers to the process by which the switch collectively realizes that something has changed in the local area network topology, and determines whether that they need to change which ports block and which ports forward. So the term convergence refers to the process of how the switch collectively realizes what's going on within that network. So that's STP's term that it uses, convergence. Okay, so it's like, okay, whoa, we have a change. All right, something's going on. Maybe an interface it has just went down. Maybe we need to make a change to our forwarding and blocking interfaces. Let's take a look. Okay, we're not receiving or getting anything from that gigabit 0-1 now. All right, we got to get gigabit 0-2 into the forwarding state. All right, let's turn gigabit 0-2 into the forwarding state now. All right. To complete the description of Stp and Rsdp does, place each ports into an either forwarding or blocking state. The more interesting question on the one that takes a little bit more time to understand is how and why Stp makes its choices. Okay, so now we're going to have to dive into how it actually decides. There's some kind of intelligent logic behind that decision. It just doesn't shoot from the hip like I usually do. Okay, it makes an intelligent decision on what ports it's going to be placing into the blocking state, what ports it's going to be placing into that forwarding state. Okay, all right. So how Stp manages to make switches block or forward on each interfaces, and how does the convergence to change states from blocking forward. Take advantage of the direct net links in response to a network outage. All right, that's cool. All right, clear my board real quick. All right, how Stp tree works. All right, spanning tree. How does spanning tree work? The Stp algorithm creates a spanning tree of interfaces that forward frames. The tree structure of forwarding interfaces creates a single path to and from each Ethernet link, just like you could trace a single path single path in a living, growing tree from the base of the tree to each leaf. So it's just a simple. Here we go. All right. Here's our tree. Here's our, here's the root of our tree. We got the root of our tree right here. All right. Now we got little branches. Here's our leaf. All right. And we got a leaf over here. All right. These are nodes. All right. These are switches. All right. All right. So what it's using that same type of logic. All right. It starts at the root and it goes from there. All right. Starts at the root and goes from there. All right, that's where it comes up with that spanning tree name. All right, it's using the logic of how a tree is actually constructed. Okay, every tree has a root. All right, and then from there, that tree splines out. It splines out in multiple directions. But no matter what, it always has to. Every branch comes back to its root. Every leaf comes back to every leaf goes back to a branch that goes back to the root. All right, a leaf cannot be without an actual root of that tree. It cannot live. All right. All right. Take a deep breath. All right. Stp was created before local area network switches ever existed. Using LAN bridges to connect LANs today, switches play the same roles as bridges. So, you're going to continue to hear the terminology bridge as we continue on here. Root bridge and stuff like that. Now, bridges have switches were bridges. Well, bridges. let me see. It was bridges, hubs, and switches. I believe that's how the lineage of a switch came from. But either way, some of that same logic of what a bridge used to be is some of the same logic that these switches still hold. Okay. Implementing, however, many STP terms refer to bridge. That's why you're going to continue to hear that same terminology, bridge. All right. Even though we're talking about switches, all right, you're going to continue to hear terminology bridge. So as we continue on our chapter, let's just get it clear now that when we say bridge, we're talking about switches. Even though we're talking root bridge, we're talking root switch, which is the root switch. We're not talking about a actual bridge device. We're still referring to a layer 2 switch or a layer 3 switch. Well, for now, we're still talking about layer 2 switches, all right? So let's just make that clear. All right. The process used by STP, sometimes called spanning tree algorithm, STA, all right, chooses the interfaces that should be placed in the forwarding state. For any interfaces not chosen to be in the forwarding state, STP places the interfaces in the blocking state. Okay. In other words, STP simply picks which interface should forward, and any interfaces left over block. So it just says, okay, are these the only interfaces I need? If those are the only interfaces I need, everything else is going to be blocked. Very simple. All right. Excuse me. STP uses three criteria to choose whether to put an interface into the forwarding state. STP elects a root switch. All right. STP puts all working interfaces on the root switch into the forwarding state. So we're going to elect a root switch. One of our switches inside of our topology, all right? One of these switches is going to be our main man, all right? STP is going to choose out of these switches which one do I want my root switch to be. Once it does all of its thinking, it says, okay, you're the one, XW1. All right, it's going to say you are now root. All right. Once switch 1 becomes root, all of its ports are in the forwarding state. All right, forwarding state. All right. All of its ports are in the forwarding state. It's not blocking any of the ports on the root. None of the ports on the root will be blocked. They're all going to be in the forwarding state. Okay? Each non-switch considers one of its ports to have the least administrative cost between itself and the root switch. That cost is called switch root cost. STP places its ports that is part of the least root cost called the switch root port, all right, in the forwarding state. So what it's going to say now is, okay, we have our switches. We have S2 and S3 over here. All right. We have a link from S3 going to switch 1. We have another link going from switch 2 to switch 1. Okay. Then we also have this link over here. All right, going from switch 2 to switch 3. All right. What it's going to say is, all right, out of all these connections that we have on S2 and S3, so we have 1, 2, 3, 4. We have 4 connections now. All right. It's not going to block anything on the root. All right, but it has to select one of these ports, all right, on either one of these switches to block. It has to block one of them, all right? So there's going to be a cost behind there, all right? Now, if we're looking with our human eyes, okay, we're looking at this from our direction, all right, we can almost tell what's going to be the lowest cost. So from switch 1 to switch 3, all right, which one is going to be, is it going to take the route from switch 3 to switch 2 to switch 1? I don't think so. I think it's going to take the switch 1 to switch 3's interface All right, and it's gonna put this interface right here in the forwarding state. Now, if switch 1 wanted to talk to switch 2, should it have to go to switch 3 and then down to switch 2? No. I think it's just going to go to switch 1 to switch 2, okay? So it's going to choose this to be in the forwarding state. All right? Now, again, we're just looking at this from a high level, okay? That's why it's kind of easy for us to decide now. All right. Now, since we've kind of figured out that these two, you know, from our direction on how we're observing this, it's going to be pretty easy for us to decide, okay, since we have these two as the shortest path to switch 1, so our connections on switch 3 and switch 2 that are in the longest path, we're going to say longest path, but there's going to be a map that is going to show us here shortly. We're going to have to say these two are now going to be in our blocking state, okay? Because it would cost switch 1 a longer time to, again, if it had to go to switch 1 to get a message to switch 3, it's not going to go to switch 2 and then to switch 3, all right? It's going to go from switch 1 to switch 3, all right? Same thing. It's not going to go from switch 1 to switch 3 to switch 2. It's going to go from switch 1 to switch 2, all right? So it is going to decide interfaces on the designated. So root, all right? And then these are not going to be root ports. These are the root ports on those other switches, root ports, all right? All right? These are the root ports because these are the ports that are going back to root, okay? All right. Let's continue on. All right. Note, the real reason that the switch places all working interfaces in the forwarding state at step 1 is that all interfaces on the root switch will become DP, designated ports. All right, DP, designated ports. All right, don't get twisted thinking DP for another thing. All right, DP, designated ports. All right. However, it's easier to just remember that all the switches interfaces are on the forwarding state. So we have root ports on that are not, these root ports are not on the root switch, okay? The root switch has designated ports, DPs, designated ports. The interfaces on the root switch has the designated ports. The other switches have the root ports, okay? All right. Let's keep it moving. It's just going over some of the characteristics here. All right. All right. Stp. Hold on 1 second. Take this phone call real quick, guys. Important phone call for me. Hello, it's Joe. All right, sorry about that. Just had a phone call I had to take real quick. All right, let's get back into it. All right, so, yep, we talked about. So where do we leave off? All right, Stp only considers working interfaces those in the connected state. Failed interfaces, for example, interfaces with no cables installed or administratively shut down, are instead placed in an Stp disabled state. So the section uses the term working ports to refer to interfaces that could forward frames if Stp places the interfaces in the forward state. All right, let's read the next note. Next note, Stp, Rsdp do differ slightly in the use of names. Remember when we were getting questions about the names between Stp and Rsdp? Some states like blocking and disabled with Rsdp using this with the status term discarding. So Stp, blocking and disabled. Rsdp uses the terminology discarding. However, those minor differences do not change the meaning of the discussion in the first section of this chapter. The upcoming section, the titled Comparing Stp, Rsdp, discusses these differences, both important and minor. Okay, so it's just some minor stuff. All right. The Stp bridge ID and hello BDUs, BPDUs. All right. The STA, the spanning tree algorithm, begins with an election of one switch to the root switch. Now, to better understand this election process, you need to understand the Stp, Rsdp messages sent between the switches, as well as the concept and formulate, as well as the concept and format of identifying used to uniquely identify each switches. The Stp Rsdp bridge ID, PID, the bridge ID, is an 8-bit value unique to each switch. The bridge ID consists of 2 bytes and 2-bit priority field and a 6-byte system ID. So that's what creates that 8-bit value. Okay, it's 2 bytes in the priority field and 6 bytes in the system ID. All right. With the system ID being based on the universal burned-in address, the MAC address. All right, your MAC address is universally unique to each device. Okay, and the switch using the built-in MAC address, assuring that the switches all have a unique address. Yep. All right. Stp defines messages called root protocol data units. So bridge protocol data units. I keep saying root. Bridge protocol data units. Let's write that down. So just so I can build that into my memory. PBDU. We're going to say bridge protocol data unit. All right. Bridge protocol data unit. Cool. BPDU, bridge protocol data unit. PBDU, bridge protocol data unit. Perfect. Got it in my memory now. I'll stop saying bridge now. All right. I'll stop saying root. Whatever. All right. All right. Root bridge ID. The root bridge ID of the switch, the sender of the hello currently believes to be the root switch. Sender bridge ID, the bridge, sender root cost, timer value. All right. For the time being, just keep the first 3 items on the table in mind as the following sections work through the 3 examples of how Stp chooses the interface to be placed in the forwarding state. Next, in the text examines the 3 main state steps of Stp and Rsdp. Electing the root switch. All right. Switches elect a root switch based on the BIDs, so the bridge IDs. All right. In the BPDUs, the bridge protocol data units. All right. The bridge protocol data units. the root switch is the switch with the lowest numeric value in the BID, the BIDs, all right? Because of the two-part BID, starts with the priority value. So because the two-part BID starts with the priority value, essentially the switch with the lowest priority becomes root. For example, if a switch has a priority value of 4096 and another switch has a priority of 8192, the switch with the priority value of 4096 wins, regardless of what MAC address was used to create the BID for each switch. So regardless of the MAC address, if the priority level is lowest, that switch is gonna become the root switch. All right. But now it's gonna talk about if there's a tie on that. If a tie occurs based on the priority portion of the BID, the switches with the lowest MAC address portion of the BDU is root. So again, the switch with the lowest MAC address portion in the BDU is root. So if there's a tie in the BIDs, all right, then it's going to take a look at the MAC address. The switch with the lowest numeric MAC address from there is going to win, again, the election. Okay? No other tiebreakers should be needed because switches use one of their own universally built MAC addresses as the second part of the BIDs. So if the priority ties and the switch uses the MAC address of all 02.all O's as part of the BID, and the other one uses the 811.11.11.11, the first switch with the 02 all zeros becomes the root switch. All right. Let's keep it moving. Stp Rstp elects a root switch in the manner not unlike a political election. The process begins with all switches claiming to be the root by sending the BPDUs listing their BIDs as the root. If the switch is here, all right, this is when it's in the listening phase, okay? All right, the STP is listening for those PPDUs, all right? That's what it's doing, all right? If the switch hears a hello that lists a better, lower, all right, a lower, better meaning lower BDU, the switch stops advertising itself and starts forwarding the superior hello messages. So, again, here's our switches. All right, all these switches are starting to forward their BIDs. All right, it's going to forward those PBDU. All right, the messages. All right. Switch 1's going to say I'm root. Switch 3 is going to say I'm root. Switch 2 is going to say I'm root. All right. What's going to happen is when switch, and it's going to send it in this direction too as well. All right. So if switch 2 gets the message from switch 1, and switch 1 has a lower BID than switch 2, all right. Switch 2 is going to say, okay, you won switch 1. Now let me send those messages off to switch 3. All right, saying that you are the superior now. All right. And then switch 3 is still going to be sending its messages saying I'm root. I want to take over. So then it's going to do its comparison. Once it's done its comparison to switch 1's PIDs and itself's PIDs, then it's going to make the election from there. And then obviously, if switch 1 has the lowest priority or lowest numeric MAC address, it's then going to become the root switch. All right. So that's how it's making these decisions, guys. All right. A better hello, meaning that the list root BDUs is better, pretty much numerically lower. All right. Better is lower. It's called a superior hello, or a worse hello, meaning that the list with the root bridge is not good, numerically higher. All right. It's called an inferior. So we have superior and inferior. All right. Hello messages. All right. The figure shows the election and how the election is being taken place. So So here's my PDU, my BDU, BID. So here's my BID. All right. So my BID is 32769. All right. It's sending that message off to here. All right. And it's saying, okay, mine is 307069 and mine is 307069. All right, cool. Now we have to look at MAC addresses since all the priorities seem to be the same. So let's take a look at MAC addresses. My MAC address on route 1 is 02 0001 0001. Mine is 02 00 002 002. Okay, cool. Mine is 003 003. So automatically, if you can take a look at these at these MAC addresses, okay, you can already start seeing what route bridge, what it's going to choose. Okay, it's going to choose the route bridge first off with the lowest priority, and they all seem to have the same priority. All right, that's fine. So then it's going to look at the MAC addresses. Let's take a look at the MAC addresses, and then it's going to take it. It's going to choose which bridge has that, which switch has that lower MAC address. All right, from there. All right. Yep, kind of touched on that. All right. Key topics, lowest priority. If there's a tie, lowest switch MAC address. Okay. So remember, lower is better. Lower priority number will win. And then if there's a tie, the lowest MAC address, the lowest numeric MAC address will win. Okay. Choosing each switch route port. The second part of the Stp and Rsdp process occurs when each non-root switches choose its one and only root port. All right. A switch's root port is an interface through which it has the least cost to reach the root switch. So it has the least cost to reach the root switch. All right. The idea of the switch cost to reach the root switch can be easily seen for humans. Again, as we can look from a higher level. All right. Just look at a network diagram that shows the root switch. List the Rsdp cost associated with each switch port. Identify the non-root switch in question. The switch uses different process than looking at the network diagram. Of course, by using a diagram can make it easier to learn the idea. So, exactly what we were saying before. Now it's implementing an actual. It's giving it an actual physical cost now. Okay, so for switch 2 to switch to reach S1. S1 is root. Remember, S1's root. A lower cost to reach it in this direction. Okay, let me erase that real quick. All right. So again, there's a lower cost in this direction. A lower cost in this direction. Okay. Now, switch 2 wouldn't go from switch 3 just to reach to root. All right. Same thing. Switch 3 wouldn't go in this direction to switch 2 to then get back to root. Okay. This is a higher cost. All right. There's more traveling involved in that cost right there. Okay. So that's the logic. Okay. All right. Let's keep it moving. All right. Switch comes to the same conclusions, but using a different process. Instead of adding their local, instead they add their local interface Rsdp cost to the root cost listed in each received hello PDU. The Stp Rsdp port cost is simply an integer value assigned to each interface per VLAN for the purpose of providing an objective measurement that allows Stp to choose. Okay, so the port cost is a simple integer value assigned to each interface per VLAN for the purpose of providing an objective measurement that allows Stp to choose. All right. So it's a simple integer value assigned to that interface per VLAN, all right, that allows for objective measurements. Okay. All right. That's how that's how this algorithm works. Okay. All right. The figure shows an example. The example how the switch calculates their best root cost and chooses the root port using the same topology Sdp cost. In Figure 9, switch 1 calculates the cost over the root. Two possible paths by adding the advertising the two interfaces in the list. Okay. So it's just advertising the cost here. It's figuring out that cost. Once that cost is figured out, it figures that, all right, now this is my root port. This is my root port. All right. And these right here are going to be my blocking ports on those two switches. Okay. All right. How Stp actually calculates the process. Yep. All right. Focus on the moment of the root switch sends the other. All right. All right. Covered that pretty well. All right. Choosing the designated port of each LAN segment. Stp Rstp found in final step to choose the Stp Rstp topology is to choose the designated port on each LAN segment. The designated port on each LAN segment is the switch port that advertises the lowest cost hello onto the LAN segment. When a non-root switch forwards a hello, the non-root switch sets the root cost field in the hello to the switch cost to reach the root. In effect, the switch with the lower root cost to the lowest cost to reach root among all switches connected to the segment becomes the designated port on that segment. All right. For example, in the figure shows in bold text the part of the hello message from both switch 2 and switch D to determine the choice of the designated port on the segment. Note that both SW2 and SW2 list their respective costs to reach the switch port. Cost is for cost on cost 4 on S2 and cost 5 on S3. Switch 2 list the lower cost. So S2 gigabit 0-1 is the designated port on the local segment. All right. So it's just showing the cost here. So again, remember that it's applying these integers, all right, to be objective. So it can figure this. So Stp can figure this out. All right. So obviously on the gigabit 0-2 here, it's stating a lower cost. Okay, a lower cost value. All right. All right. Yep. All right. Note, 2 additional tiebreakers are needed in some cases, although these would be unlikely today. A single switch can connect the 2 or more interfaces to the same collision domain by connecting to a hub. In that case, the switch has its own PBDUs. So if a switch ties with itself, 2 additional tiebreakers lose the lowest interface Rsdp priority, and if that ties the lowest internal interface number. All right. So it takes steps if there is more, if it needs to continue to do tiebreakers. Okay. All right. The only interface that does not have a reason to be in the forwarding state on the 3 switches in the example shown in 5.3 through 9.6 is the switch 3's gigabit 2 port. All right. So that's this port right here. All right, guys, this port right here. All right. All right. So the Stp process is now complete. The table below outlines the state of each port and shows why it's in its state. So, so it's pretty much stating these are both on SW1. All its interfaces are in the forwarding state. Those are designated ports, obviously. The interface that's going to the root switch, all right, that is the root port, all right, and the gigabit 0-1 is the designated port on the LAN segment. So that it is designating a port on the LAN segment to switch 3. All right, the switch 3. All right, the switch 3 is gigabit 0-1 is in, again, that's the root port. All right, and then the gigabit. So it's pretty much stating that this will be the blocking. This will be blocked. So this will be blocked. All right. Let me make this smaller. All right, this is Stp on the LAN segment. All right. This port right here is RP, root port. All right. This one is root port as well. All right. And these are both DP, designated ports. All right. DP. All right. Because this is the root bridge. All right. This one right here would be blocking. All right. All right, configuring to influence the Stp topology. Stp works by default on Cisco switches, so all the settings needed by a switch have a useful default. Switches have a default BID based on the default priority value, and adding the MAC address that comes with the switch's hardware. So it already has all of that. By default, it has all of this information already built into it. All right. Additionally, switch interfaces have default Sdp cost based on the current operating speed of the switch's interface. Network engineers often want to change the Sdp settings to change the choice of the Sdp makes it give in a given local area network. The two main tools available to the engineers are to configure the bridge ID and to change the root cost, the port cost. All right, so we can change the bridge IDs to a lower bridge ID. All right, and we can change the port cost. Okay, so we can alter these two states so we can define where we want the root bridge and where we want the what ports that we actually want to be designated ports, root ports, or blocking ports. Okay, so we can define all of that stuff ourselves. Okay, we can statically do some of this stuff. Okay, first, to change the bridge, the BID, the engineer can set the priority used by the switch while continuing to use the MAC address as the final 48 bits on the BID. For instance, giving the switch a lower priority value among all the other switches will win the root election. So remember, it looks at the first part. It looks at the priority value first before it looks at the MAC address. All right. So if we statically alter the priority value on a particular switch, we can make that switch the root switch. All right, because remember, it looks at that first. It looks at the first part, which is the priority cost. Okay. All right. The port cost also has a default value per port. Per VLAN, you can configure these port costs, which will in turn impact many switch calculations of the root cost. For instance, to favor one link, give that port on that link a lower cost. To avoid a link, give that port a higher cost. So we can alter the cost of these ports to either to ensure that it becomes the designated port or the root port, or to ensure that it becomes, a blocking port or a designated port. Okay. All right. Of course, it helps to know the default cost values, so you can then choose alternate values as needed. The table lists the default port cost suggestions by the IEEE. iOS on Cisco switches has long used the default settings as defined as far back as 1998 version of the IEEE 802.1 Delta standard The latest IEEE standard suggests Rsdp default cost as the publication, as of this publication, and the book, the 2008 publication, the 802.1q standard suggests values that are more useful when using links faster than 10 gigabytes per second. Okay. All right. So here's a quick table on some of our costs here. All right. So before, all right, 1998 and 2004. So they had to increase the actual cost range. They had to increase the cost range because back then, what are you doing, Melissa? Back then, obviously, 100 gigabytes per second and 1 terabyte per second speeds weren't considered yet. They weren't considered to be a factor inside of the networks yet. But now, obviously, as we're progressing in our technology and things are progressively getting faster, they had to compensate for those faster range of speeds on these interfaces now, and so they had to increase the cost range. Okay, they didn't change anything else besides they increased the cost range. All right, so that's why you see back in 1998, this would be the default cost for a 10 megabyte per second. I just highlighted that, didn't I? All right, 10 megabytes per second interface. Okay, but now that cost is now at, you can set it to 2 million now. All right. All right, so you have a wider range of how you are altering the cost on these ports. Okay, all right. Note in regards to these defaults, the cost default based on the operating speed of the link, not the maximum speed. That is if a 10-100-1000 port runs at 10 megabytes per second for some reason, its default STP cost on a Cisco switch is 100. The default cost for the running for an interface running at 10 megabytes per second. Also, if you refer to the default on the right column, note that Cisco Catalyst switches can be configured to use those values as default with a single global configuration command, spanning tree path cost method long. All right, so if we want to use the new IEEE standard, we would just have to use we would go into global configuration mode and we would set it at the spanning tree port path cost method long. So we can set our Cisco switches to use these ranges, all right? But by default, it's still using these ranges right here, okay? All right? All right, detail specifics to STP, not Rsdp. So here we go. So we're going to touch on some of the differences now. As promised in the introduction to this chapter, the first section showed features that apply to both Stp and Rsdp. This next heading acts as a turning point, with the next several pages being about Stp only. The upcoming section, Rapid Stp Concepts, then show us details specific to Rsdp and those in contrast to Stp. Once an engineer has finished all Stp configurations, the Stp topology should settle into a stable state and not change, at least until the network topology changes. So unless something was to happen, you had a failure on an interface, until that point, once it settles, that's it. This section examines the ongoing operation of Stp while the network is stable, and then it covers how Stp convergence to a new topology when something changes. Note that almost all the differences between Stp and Rsdp revolve around the activity of waiting for and reacting to changes in topology. So let's say that again. Note that almost all differences between Stp and Rsdp revolve around the activity of waiting and reacting. So that's where a lot of these changes come into play. Is in Stp and Rsdp is when they're in the waiting and reacting phase. Okay, Stp perform well in error in circumstances in which it was created. The rapid in the Rsdp refers to the improvements to fast Rsdp, how fast Rsdp can react when changes occur. So understand how Stp reacts will ensure to understand why Rsdp reacts faster. The next few pages should should show the specifics of Stp and not Rsdp, and how Stp reacts and manages convergence when changes happen in an Ethernet LAN. All right. Stp active activity when the network remains stable. An Stp root bridge sends a new hello PDU every 2 seconds by default. So remember, back in the beginning, those hello messages, all right, those are set. That timer is set by the root switch, all right, and by default, it's every 2 seconds. But we can change that. We can alter that, all right. But by default, it's every 2 seconds. But that timer is set by the root switch. So if we were to change that on the root switch, that timer would change for everything else. Okay. All right. Each non-root switch forwards the hello on all designated ports, but only after changing only after changing items listed in the hello. As a result, the hello flows once every working link in the local area network. When forwarding the hello BPDUs, each switch sets the root cost to the local switch's calculated root cost. The switch also sets the sender bridge ID field to its own bridge ID. The root bridge ID field is not changed. Assuming all default hello timers of 2 seconds on the root bridge, each switch would forward the receiving and not change hellos out all designated ports, so that the switches continue to receive hellos every 2 seconds. All right. The following steps summarize the steady state operations when nothing is currently changed in Stp topology. Okay. So some key topics. Step 1: the root creates and sends a hello PBDU with the root cost of 0 out all of its working interfaces. The non-root switches receive the hello on their root ports after changing the hello to list their own BIDs as the sender BIDs, and list that the switch's root costs. The switch forwards is the hello out all designated ports. So it receives those hello messages on its root port, and forwards them out its designated port. So again, you got root. Root's going to send those hello messages out. S3 is going to get a copy on its root port, all right? But since it's blocked on its other interface, that's it. That's all as far as it's going to go. But switch 2 is going to get it on its root port, okay? And it's going to send that out its designated port, all right? And that's just how it works, all right? All right. And then obviously it's doing that to see if anything's changed within the network. So step 3, step 1, and step 2 repeat until something changes. When a switch fails to receive a hello, it knows a problem might be occurring in the network. Each switch relies on these periodically received hellos from the root as a way to know that its path to each root is still working. When a switch ceases to receive the hellos or receives a hello that lists different details, something has failed. So the switch reacts and starts the process of changing the spanning tree topology. All right, so it starts its convergence and its selections all over again. All right, Stp timer that manages Stp convergence. For various reasons, Stp convergence process require the use of 3 timers listed in the table. Not that all switches use note that all switches use the timer as dedicated by the root switch, okay? Which the root switch lists in its periodic hello PBDU messages, okay? So we have the timer. So every 2 seconds, the time period between hellos created by the root. We have max age, 10 seconds. All right, 10 times hello. All right, how long any switch should wait after ceasing to hear hello before trying to change the Stp topology. Forwarding delay, 15 seconds. Delay that effect of that process that occurs when an interface changes from blocking state to a forwarding state. A port stays in a interim listening state, all right, and then in interim learning state for a number of seconds defined by the forwarding delay. All right. Grab some water real quick. All right. All right. Let's continue on. If a switch does not get an expected hello PPDU within the hello time, the switch continues as normal. However, if the hellos do not show up again within the max time, the switch reacts by taking steps to change the Stp topology. With default settings, max age is 20 seconds, 10 times the default hello timer of 2 seconds. Okay, so a switch would go 20 seconds without hearing a hello before reacting. So it would go twice as long as you have the hello interval set. So that's how that math works. Okay. After max age expires, the switch essentially makes all its Stp choices again based on any hello it gets or receives from other switches. It reevaluates which switch should be the root. If the local switch is a non-root, it can choose its root port, and it determines whether it's designated port on each of its links. So it starts going through all those decisions all over again. The best way to describe Sdp Convergence is to show an example using the same familiar topology. The figure shows the familiar figure with switch 3's gigabit 0-2 in the blocking state, but switch 0-1 interface has just failed. So it's pretty much stating that on root, the gigabit 0-2 interface has just failed. Okay, so now it's not getting these messages now. Okay, all right. So now it's gonna start going through all of its convergence all over again. All right. In this scenario, S3 reacts to the change because S3 fails to receive its expected hello on gigabit 0-1. However, S2 does not need to react because S2 continues to receive its periodically hello on the gigabit 0- interface. That's the root port interface going to root. Okay. All right. In this case, S3 reacts either when the max age time passes without hearing hellos, or as soon as S3 notices that the gigabit 0-1 has failed. If the interface has failed, the switch can assume that the hellos will not arrive in the interface anymore. Now that SW3 can act, it begins by reevaluating the choices of root switch. S3 still receives the hello from S2 as forwarding from root SW1. SW1 still has a lower BID than SW3. Otherwise, S1 would not have already been root. All right. So S3 decides that SW1 wins the root election and that SW3 is not root. All right. Next, S3 evaluates the choice of root ports. All right. At this point, SW3 is receiving hellos only on one interface. So again, remember, even though that interface, that port is in the blocking state, it's still receiving these messages. Okay, and this is the reason why it's still receiving these messages. Okay. Next, SW3 reevaluates its root port. At this point, SW3 switch 3 is receiving hellos only on one interface, gigabit 0-2. Whatever the calculated root cost, gigabit 0-2 becomes S3's new root port. All right. The cost would be 8, assuming that Stp cost has not changed since the last figure. Switch 3 then reevaluates its role as designated port on any other interfaces. In this example, no real work needs to be done. Switch 3 already is designated port on FA013 and continues to be the DP because no other switches connect to that port. And that's, so it's just stating that in this scenario, obviously we have, it's not getting these messages anymore. So what's going to happen is gigabit 0-1, obviously it's not receiving these messages anymore. So it's going to take gigabit 0-2 and it's going to turn that into the root port now. Okay. All right. This is going to be root port. All right. All right. And obviously 5013 is just going to maintain itself as being the designated port because nothing else has changed. It's not connected to another switch. You haven't added anything to the network, obviously, or nothing like that. It just has to make switch 3 has to make a choice now to figure out, okay, since I'm not getting any more messages from this interface, I have to change my root port because obviously in gigabit 0-1, there's nothing coming from anybody anymore. So that's all it's doing. It's making a choice now to switch over. So, all right. Changing interface states with Stp. Stp uses the idea of roles in states. Roles like root ports and designated ports relate to how Stp analyzes the local area topology. States like forwarding and blocking tell a switch whether to send or receive frames. When Stp Convergence, a switch chooses new port roles, and the port roles determine the state, either forwarding or blocking. Okay. Switches using Stp can simply move immediately from the forwarding to blocking state, but they must take extra time to transition from blocking state to forwarding state. So they can immediately move from the forwarding state to the blocking state. But because of that timer, all right, when it has to wait twice the amount of the PDU message timer, all right, so if it's set at 2, all right, it has to wait twice that amount, so it's going to wait 20 seconds. It has to wait that time to consider itself when it's already in the blocking phase to move into the forwarding phase, okay? So from forwarding to blocking, it can happen immediately. But from blocking to forwarding, there's a time frame that it has to wait until that point, okay? All right? They must wait that extra time to transition from blocking state to forward. For instance, when switch 3 in the figure formerly used gigabit 0-1 as its root port, the port was in the forwarding state. After convergence, the gigabit 0-1 might be either a root or nor designated. The switch can immediately move the port to a blocking state. Okay? All right, so remember, it can move forwarding to blocking almost instantly. But from blocking to forwarding, it has to wait. There's that convergence, there's that timer. There's a certain timer it has to wait until it can go from the blocking to a forwarding state. Okay? However, when a port then formally blocks, when a port that formerly blocked needs to transition to a forwarding state, the switch must first put the ports through the two intermediate interface states. This temporary Stp state helps prevent temporary loops. Again, you don't want the switch. You don't want switch 3 to immediately switch gigabit 0-3. You don't want it to immediately switch from blocking to forwarding. All right, because what if all of a sudden on its gigabit 0-1, it then receives a frame out of nowhere. All right, and now you have gigabit 0-3 as a forwarding port now too. So now you got both these ports now forwarding frames, and now you're going to create a loop. That's why there's that timer that states that it can, from forwarding to blocking, it can be immediate. But from blocking to forwarding, you got to wait. You got to wait because we don't want to send a temporary, we don't want to create a loop within this network. That's what we're trying to prevent. So that's why it has that state. All right. All right. So key topics. All right. Listening, learning. So listening, like the blocking state, the interface does not forward frames. The switch removes old, stale, unused MAC address table entries from which no frames are received from each MAC address during this period. These stale MACs table entries could be caused by temporary loops. So while in that listening, while Stp is in that listening, all right, mode, while it's doing its convergence, it's listening. It says, okay, let me clear my MAC address table. I don't want this MAC address table no more. All right, just in case it's wrong. All right. I don't want to become famous and by my followers. All right. So, yeah. So in that listening phase, it says, all right, let me get rid of this MAC address table, just in case it might not be correct. Okay. The learning interfaces in the state still do not forward frames, but the switch begins to learn MAC addresses from frames received on the interfaces. So it starts receiving those frames. So it starts receiving frames, all right, and it's learning. It's saying, okay, cool. I'm getting these frames. Okay, my MAC address table is cleared. I'm getting these frames now. Let me start building my MAC address table from these source MAC addresses coming from these interfaces. I'm not going to forward anything yet, though. I'm not going to forward any of these frames. I just want to learn. I want to learn where these frames are coming from. I want to know if they're coming from gigabit 0-2. I want to learn if they're coming from gigabit 0-1, and then I'm going to start building my MAC address table from there. All right, before I even forward anything. Okay, listening and learning. Okay. Oh, wet my whistle. All right. All right. Stp moves an interface from blocking to listening, then to learning. Okay, blocking to listening, then to learning. All right, and then to forwarding state. All right, so we're blocking. We're not allowing any frames. Not allowing anything. All right. Then we're listening. So then, okay. So we're going to listen now. All right, we're listening and we're learning. All right. Then after we've learned, then we can start forwarding frames. Okay. All right. Stp leaves the interface. Leaves an interface in each interim state for a time equal to the forwarded delay timer, which defaults to 15 seconds. As a result of the convergent event that causes an interface to change from blocking to forwarding require 30 seconds. The transition from blocking to forwarding, in addition, a switch might have a wait max age, default 20 seconds, before choosing to move an interface from the blocking to the forwarding state. Okay? All right. For example, follow what happened in the initial Stp topology shown in figure 9.3 through 9.6. Switch 1, switch 2 links fail. All right. If switch 1 simply quit sending hello messages to S3, but the link between the two did not fail, S3 would wait the maximum age setting before reacting. Switch 3 would eventually quickly choose its port, Stp role, but then wait 15 seconds to listen and learn. So it's just stating that whole time period pretty much resulting in a 50-second convergence delay. Okay. All right. Yep. So here we go. We're going to touch on rapid spanning tree concepts. All right. The original Stp worked well, given the assumptions about networks and network devices in that era. However, as with any computing or network standards, as time passes, hardware and software capabilities improved. So new protocols emerged that took advantage of those new capabilities. For Stp, one of the most significant improvements over time has been the introduction of Rsdp, Rapid Street Protocol, introducing the standard to the IEEE. Remember, the IEEE 802.1W was the amendment that the IEEE did first. It amended to the 802.1 Delta. It amended with the 802.1 Whiskey. All right. But then it went back and created, and then it introduced Rapid Street Protocol back into the standard of the 802.1 Delta protocol. Okay. Note, just to make sure you're clear about the terminology throughout the rest of the chapter, STP refers to the original STP standard, and the use of Rsdp does not include STP. Okay, cool. Before getting into details of Rsdp, it helps to make sense of the standard numbers of bits. The 802.1 Whiskey was actually an amendment to the, yep, we just touched on that. Yeah, okay. All right, let's compare STP to Rsdp. Our Rsdp works just like STP in several ways, as discussed in the first major section of this chapter. To review, Rsdp and STP elects the root switch using the same rules. All right, it uses the same rules. Rsdp and STP select their root ports with the same rules. All right, STP and Rsdp elects designated ports in each LAN segment with the same rules. STP and Rsdp place each port in either the forwarding or blocking state, although Rsdp calls it blocking state disregarding. So, Rsdp calls the blocking state disregarding. So we have forwarding and disregarding. So we have forwarding and blocking in STP, and we have forwarding and disregarding. Okay? In fact, Rsdp works so much like STP that they could both be used in the same network. Rsdp and STP switches can be deployed in the network with Rsdp features working in switches that support it, and traditional STP features working in the switches that support only STP. With those similarities, you might wonder why the IEEE bothered to create Rsdp in the first place. The overriding reason is convergence. All right, it's convergence. All right, STP takes a relatively long time to converge, 50 seconds with the default setting when all wait time must be followed. So 50 seconds. Remember when we talked about that failure we had. Okay. All right. STP improved network conversion when topologies changes occurred, usually converging within a few seconds or in a slow condition in up to it. So we go from 50 seconds to 10 seconds. All right. So we made a big leap. All right. Rsdp changes and adds to STP in ways that avoid waiting on STP timers, resulting in a quick transition from the forwarding to disregarding. Okay, remember, we have to kind of take a step back when we're talking about blocking. We're going to say disregarding now. All right, or vice versa. Specifically, Rsdp compared to STP defines more cases in which the switch can avoid waiting for the timer to expire, such as the following. All right, key topics. Rsdp as a mechanism in which switches can replace its root port without waiting to reach the forwarding state in some conditions. So it adds a mechanism in which a switch can replace its root port without waiting to reach a forwarding state. All right. Rsdp adds a new mechanism to replace a designated port without any waiting to reach a forwarding state. Rsdp lowers waiting times for cases in which Rsdp must wait for a timer. Okay, just makes things, it's rapid. It's just making rapid decisions, but it's adding mechanisms to allow to make those rapid decisions. It's not just making decisions faster to create problems. It's just adding to what STP was already doing so we can make decisions faster. Okay, so it's just an advancement to STP. It's adding to what STP has already done, but it's just made these processes, okay, of going from forwarded to disregarding in a faster way. Okay, for instance, all right, imagine a failure case in which a link remains up, but for some reason an en route switch stops hearing the hello, the BPDUs it had been hearing in the past. Stp requires a switch to wait for a max age seconds. With Stp defines based on the 10 times the hello timer. So remember, 10 times the hello timer. By default, it's 2 seconds. So it has to wait 10 times the hello timer. So it has to wait the 20 seconds. All right. By default, Rsdp shortens that time, defining the max age timer as 3 times the hello timer. All right. Defining the max age as 3 times the hello timer. Additionally, Rsdp can send messages to the neighboring switch to inquire whether a problem has occurred rather than to wait for timer. So instead of it waiting to that max age timer, it's going to start sending messages throughout that port to see if there's a problem. Okay. The best way to get sense of this mechanism is to see how Rsdp alternate ports and backup ports both work. Rsdp uses the term alternate port to refer to a switch others ports that could be used as a root port if a root port were to fail. So an alternate port refers to a switch's others port that can be used as a root port if the root ports were to fail. The backup port concept provides a backup port on the local switches for designated ports. So the backup port concept provides a backup port on the local switch for designated ports. So backup, think designated. Alternate, think root. All right. Note that backup ports apply only to designs that uses hubs. All right. So they are unlikely to be used in today. So again, alternate ports are probably what you're going to be thinking of. Okay, not backups. All right. As hubs slowly start to leave most enterprises' networks and whatnot. All right. However, both are about how Stp works. Okay. All right. Root ports that begin a new root port. Yep. All right. Rsdp differs from Stp in a few other ways. For instance, with Stp, the root switch creates a hello with all other switches, updating and forwarding the hello. Alternately, how did I go with that? All right. For instance, with Stp, the root switches create a hello with all other switches, updating and forwarding the hellos. With Rsdp, each switch independently generates its own hellos. Okay. Additionally, Rsdp allows for queries between neighbors rather than waiting for timers to expire, as a means to avoid waiting to learn information. These types of protocols change how Rsdp based on switches isolated what has changed in the network and to react quickly. So instead of Stp, where Stp, the root bridge was like the gatekeeper of sending out those hello BDUs, those PBDUs. Okay, so in Stp, the root switch would send out those, would initiate those hello PBDUs. It would sending out its 2 root ports to the other switches. Okay, those other 2 switches would then get that information and then start making decisions on to forward or to block. Okay, but those other switches, they weren't sending out their own hellos. Rsdp, though, allows those switches to send out their own hellos. Okay, so for instance, in the other, like we just looked on S3, let's mark this up. All right. So in span tree protocol, remember, root would send out those hellos. All right, those BDUs, the bridge protocol data units. All right, the hellos. All right, it would send it out by default every 2 seconds. All right, by default it would send those out. All right, it'd be sending those hellos out to switch 3 down here and switch 2. All right, so by default root was in charge of that. All right, and then once once these guys got it, you know what I'm saying, they would send out their hellos and whatnot. Rsdp though states what it's added is if something was to happen, these switches now can send out their own hellos. They don't have to wait for root to send out the hellos. They can send out their own hellos so they can rapidly make decisions on what's going on within that topology now. Okay? All right. So, let's continue on here. All right. Rsdp and alternate and the alternate port roles, root port, with Stp and with our Stp, each non-root switch places one port in the Stp root Stp root port role. Rsdp follows the same convention with the same exact rules by choosing root ports. Rsdp then takes it to another level beyond Stp, naming other possible root ports, identifying them as alternate ports. Okay. All right. To be an alternate port, both the root port and the alternate. Woo! I just got a follow. Who did I get a follow for? Crispy! Thank you for the follow. Thank you for the follow. How you doing? All right. All right. Let's continue on here. To be an alternate port, both the root port and the alternate port must receive hellos that identify the same root switch. For instance, in the figure, switch 1 is the root. All right, switch 1. Again, we're gonna go with the same thinking here. We're gonna have switch 1 as being the root. All right. Switch 3 will receive the hello PPDUs on the two ports, on its both gigabit 0-1 and gigabit 0-2. All right. Both hellos list switch 1 bridge ID as the root switch. So whichever port is not the root port that meets this criteria. So remember, when we go, it's using the same convention where it still states it's going to look for the lowest cost to get back to the root. So gigabit 0-1, it's going to be root port. And then on switch 2, gigabit 0-2 is going to be root port. All right. All right. So with those both hello messages, bridge IDs, and the switches, so whichever port is not the root port meets the criteria, will be the alternate root. So since gigabit 0-2 on switch 2 does not meet the criteria, it does not meet the specific, its cost is too high to be root. Remember, on an STP, that port, that interface is going to be in the blocking. All right, it's going to be in the blocking state. And Rsdp, it's going to be in the disregarding state. Okay, but it's also going to be it's also going to be designated to be the alternate root. And the reasoning is for that is if something was to happen on the interface gigabit 0-1 going to gigabit to the root bridge now, it needs an alternate root port. Okay, and that's when it's going to assign the alternate root port on the disregarding port as gigabit 0-2 on switches 3 interface now. Okay. All right. All right. Let's keep it moving. All right. An alternate port basically works like the second best option for the root port. All right. The alternate port can take over for the former root port, often very rapid, without requiring a wait or an interim, requiring a wait in the other interim Rsdp state. For instance, when the root port fails or when hellos stop arriving on the original root port, the switches can change the former root port role state in the man, I'm stumbling over my words now. the roll from the root port is disabled, and then the state from the forwarding to disregarding. So in other words, let me just put it in my own words. This is alternate now, okay? He's alternate, all right? What's going to happen? We stop receiving our hello messages from root, all right, on this interface, all right? Rsdp says it's going to be able to send those hello messages, all right, without waiting for, again, thinking Stp, without waiting for this whole timer for the 2 times, for the 10 times timer, all right, for the 10 times, all right, timer, all right. S3 is going to be able to send those hello messages. Since it's not receiving anything back, it's going to take its alternate route now, and then it's going to be able to start, it's going to then put that alternate route into the forwarding state, all right, without having to wait for that 50 seconds. Remember, default, waiting that default 50 seconds to complete the convergence all over again, all right? It's going to just, okay, here's alternate. We're not receiving anything. We're not getting anything back now. Now, okay, we're going to have to switch to root. Your root now, buddy, all right? So that port now is going to become root, and then it's going to be able to regain network traffic all over again, okay? What, my whistle? All right. Let's continue on here. Notably, the new root port also notably the new root port also does not need to spend time in other states, such as learning state, instead of moving immediately to port. So it doesn't have to go to that whole convergence again. It doesn't have to listen and learn and do all those steps like it did in Stp. So it is so much less that it has to do to just turn into their root port now. Okay. All right. The figure shows Rsdp's convergence. S3's port before the failure shown in this figure. The link connected directly to S1, root switch. Then S3's link to S1 fails as shown in the step. Yep. All right, so again, it doesn't have to go through the listening. All right, it's listening. It's going to go through all that time again in Stp. It's listening for those hello messages. It's not getting anything. All right, now we're going to have to go to the learning phase all over again. It's learning. All right. Now we can turn into the root. That's Stp. Rsdp states, nope, we don't have to go through any of that. All right, we're just going to switch right away. Boom, right over. Alternate. You're the new root port, buddy. Let's go. So that's what it does. All right. Rsdp states and process. The depth of the previous examples does not point out all the details of Rsdp. Of course, however, the example does show enough detail to discuss Rsdp states in the internal processes. All right, both Sdp and Rsdp uses port states, but with some differences. First, Rsdp keeps both the learning and forwarding states as compared to Stp for the same process. So it keeps both the learning and the forwarding states as compared to Stp for the same process. However, Rsdp does not even define a listening state. So Rsdp does not define a listening state. All right, finding it unnecessary. All right, so Rsdp does not find listening necessary. All right, it doesn't, because it has, since it's making choices to choose alternates, it doesn't have to wait to listen to anything anymore. It's already going to send, if it's not getting anything messages back on its root ports, because it's going to be sending its own. Remember, in Rsdp, it can send those messages on its own. It's going to send those hello messages on its own. So since it doesn't have to wait, what's the point of listening now? Okay, that's what it's stating. Okay. Finally, Rsdp names the blocking state to the disregarding state and redefines its use slightly. Rsdp uses the disregarding state for what Stp defines as the two-state disabled state and the blocking state Blocking should be somewhat obvious by now. The interfaces can work can work physically, but Stp Rsdp chooses to not forward traffic to avoid loops. All right. Stp disabled state simply meant that the interface was administrative disabled. So that's if you do the shutdown command on a particular interface. Okay, you administratively shut that interface down. You've administratively said, I don't want to use that. That interface is not to be used. You did that. Okay, you as the administrator. Okay, Rsdp just combines those into a single disregard state. Okay, that's all Rsdp is doing. It's just taking that terminology and says, okay, it's just disregarding. That's it. That's all we're gonna call it. Cool. All right. All right. Rsdp and the backups designated port. Rsdp backup roles excuse me, act as act as yet another new feature of Rsdp's port role as compared to Stp. As a reminder, the Rsdp alternate port creates a way for Rsdp to quickly replace the root ports. Similarly, the Rsdp backup port roles creates a way for Rsdp to quickly replace a switch's designated ports on some local area networks. Right? The need for backup ports can be a bit confusing at first because of the need for a backup port only happens in a design that is unlikely today. So again, we're not going to be using hubs really. You're not going to really be using hubs in your topologies these days. Okay, hubs have gone away. Okay, so the reason in this must be used for hubs, which then allows the possibilities that one switch connects to more than one ports on the same collision domain. All right. So remember, hubs use half duplex logic. Hubs use half duplex logic. So you would have to create a redundant link to a hub because half duplex. So one port is receiving messages, the other one is transmitting messages. All right, that's the half duplex logic. Okay, that's the collision domain. That's where the terminology, the collision CSMA/CD collision domain. That's why that algorithm had to be created for hub logic, for half duplex logic. All right, when you had collision domains. Okay, Rsdp is built into that so you won't create loops within those redundant links. And what it's doing with the backup, with this right here, what it's stating, the Rsdp adds the backup to port role. Just if you have a failure, again, if you had multiple, say you had 4 links to a hub, just to add some redundancy, you don't want to create. Obviously, you want some of those links to be shut down, so you're not creating infinite loops between those hubs and whatnot. This is just adding that same type of logic as it did with the root alternate and root itself, but with designated ports now. Okay, so it's now moved into the designated ports. Okay, because remember, designated ports, those ain't going to root. Designated ports are going to other devices like end devices, hubs, stuff like that. Okay. All right. Rsdp port types. The final Rsdp concept includes here relate to some terms Rsdp uses to refer to different types of ports and links that connect to those ports. To begin, consider the basic image in the figure. It shows several links between 2 switches. Rsdp considers these links to be point-to-point links. Point-to-point links. All right. So that's where the PPP comes in. Point-to-point ports. Point-to-point ports. Okay. And the ports connected to them to be point-to-point ports because of the links. Because of the link connects exactly to two devices. Okay. All right. Rsdp further classifies point-to-point ports into two categories. Point-to-point ports that connect to two switches are not at the edge of the network and are simply called point-to-point ports, PPP. All right, ports that instead connect to single end devices at the edge of the network, like PCs or servers, are called point-to-point edge ports. So we have point-to-point ports, point-to-point edge ports, or simply edge ports. Okay. In the figure, switch 3 ports connect to a PC in the edge port. Okay, cool. Finally, Rsdp defines the term shared to describe ports connected to hubs. The term shared comes from the fact that the hubs create a shared Ethernet. Hubs also force the attached switches ports to use half duplex. Remember, half duplex. Hubs use half duplex. That's where you come into the collision domains. Okay. Rsdp assumes that half duplex ports may be connected to hubs, treating ports that use half duplex as shared ports. Rsdp's convergence more slowly on shared ports as compared to all point-to-point ports. Okay, cool. Optional Stp features. To close out the chapter, the last few points introduce a few optional features that make Stp work even better and more secure. Ethernet channel, port fast, and PPDU guard. All right. Ethernet channel. One of the best ways to lower Stp convergence times is to avoid convergence altogether. Ethernet channel provides a way to prevent Stp convergence from being needed when only a single port or cable failure occurs. Okay. Ethernet channel combines multiple parallel segments of equal speed, up to 8, between the same pair of switches bundled into an Ethernet channel. The switches treat the Ethernet channel as a single interface with regard to Stp. As a result, if one of the links fails, but at least one of the links is up, Stp convergence does not have to occur. For example, in the figure shows a familiar three-switch network, but now it has 2 gigabit connections between each pairs of interface. All right, now we're getting to some of the cool stuff now, guys. Ethernet channels and stuff like that. All right, so what this is stating is, again, we have, let's draw our switches again. I'm already running out of time for another macro. So what we're adding now, okay, we're adding multiple links now. All right. So we're adding multiple links, and we're bundling them into Ethernet channels. All right. And again, say on gigabit 0-1 on switch 2, say you would have this is root port. Okay. All right. This is root port. All right, because it's going to root bridge. All right, that's the root bridge or root switch. Okay, with an Ethernet channel, if there was a failure on this link on the root switch, with Stp, convergence wouldn't need to happen. Okay, because we have a channel that this interface will still be sending those hello messages still. All right, and then this would still, because you got to think now it's bundled. It is fundamentally thinking that this is one link now. When you create an Ethernet channel, you've fundamentally taken 2 interfaces, all right, and making them one interface, all right. Logically, you've made it one interface. Okay, so even if you were to have a failure, convergence wouldn't need to happen, because logically it's still using that same Ethernet channel group. Okay, all right. Ethernet channels connect multiple parallel segments to equal speeds, up to 8, between the same pair of switches, bundling them into an Ethernet channel. The switches treat Ethernet channels as a single interface with regarding to Stp. As a result, if one of the links were to fail, but at least one link is up, Stp's convergence does not have to occur. All right. All right. There we go. Scroll down. With each pair of Ethernet links configured as an Ethernet channel, Stp treats Ethernet channels as a single link. In other words, both links in the same switch must fail for a switch to need to cause Stp convergence. So we would have to have a complete failure on one of these Ethernet channels, which is unlikely. But you would have to have a complete failure for that to happen, for convergence to happen again. All right? All right? All right. So, yeah, without Ethernet channels, if you had multiple parallel links between two switches, Stp blocks all the links except one. With Ethernet channel, all the parallel links can be up and working at the same time, while reducing the number of times Stp must converge, which in turn makes the network more available. Okay. The current CCNA exam blueprint includes a topic for configuration of both layer 2 Ethernet channels as described here, as well as layer 3 Ethernet channels described in chapter 10. All right, Rsdp and Ethernet channel configuration shows how to configure layer 2 Ethernet channels, while chapter 17, IP routing in LANs, shows how to configure layer 3 Ethernet channels. Note that layer 2 Ethernet channels combine links that switches use as switch ports with the switches using layer T switching logic to forward and receive Ethernet frames over the Ethernet channels. Layer 3 Ethernet channels also combine links, but the switches use layer 3 routing to forward packets over the Ethernet channel. So remember, we're still in the realm of layer 2 switching logic, MAC addresses, okay, frames. We haven't taken the deep dive into IP, network, packets. We haven't stepped up on that ladder yet, okay? We will here shortly, but we haven't got that far yet, okay? All right. Port fast. Port fast allows a switch to immediately transition from blocking to forward, bypassing listening and learning states. However, the only ports on which you can safely enable port fast on ports which you know that no bridges, switches, or any Stp speaking devices are connected. Otherwise, using port fast risks creating loops. Okay. Otherwise, you run the risk creating a loop. All right. The very thing that the listening and learning states are intended to avoid. All right. So you got to think. Port fast will immediately will enable a port to start forwarding frames, okay? But you got to think, you don't want to have that create a loop now. You know what I'm saying? You don't want to have port fast just overdoing what Stp is trying to avoid, and that's creating a loop. You don't want port fast to do that, okay? Port fast is most appropriate for connections to use to end devices. All right, servers, PCs, hubs, whatever. If you turn on port fast on ports connected to end devices, when an end device's PC boots, the switch port can move an Stp forwarding state and forward traffic as soon as the PC NIC is activated. Without port fast, each port must wait while the switch confirms that the port is a designated port. All right. With Stp in particular, and not Rsdp, the switch waits in a temporary listening, learning state before settling on the forwarding state. So, port fast. All right. So you got your switch. All right. You got it connected to Bob's PC over here. All right. Bob's PC. All right, and you got your other multiple links. Here you go, your other switches and whatnot. All right, when Bob's PC turns on, what port fast is going to do, all right? Because this link may not be designated, STP might have not designated this as a designated port yet. Woo woo! Purple neon, thank you for the follow. Woo woo! All right, so what port fast is going to do is, you don't want to be waiting. Bob's PC doesn't want to be waiting on STP to determine that interface, that port now, to be a designated port. All right. Port fast is going to enable it to start forwarding and receiving frames right away. So that's what port fast is going to do. Okay. It's going to just start. You're going to be able to start forwarding frames. So you don't want to enable port fast on a port that could possibly create a loop within your network. So you're not going to enable port fast on the links that you have going to other switches that STP is working on. You don't want that, all right? Because port fast will say, okay, I'm going to start forwarding frames. Well, you don't want that, because this port, STP has already put that port into a disabled or blocking state. Okay, so that's what port fast is doing. All right. Let's keep it moving. As you might guess, for the fact that port fast speeds convergence, Rsdp includes port fast. You might recall to mention Rsdp port types, particularly point-to-point edge types around the figure. Rsdp by design, the protocol converges quickly on these point-to-point edge types ports. Remember, port-to-port edge. That's going to edge devices. That's, PC servers, and then hubs. But you're not going to have, again, you're not going to be really dealing with hubs too much anymore. All right. By design of the protocol, converges quickly on these point-to-point edge types by bypassing the learning state, which is the same idea Cisco originated, introduces with port fast. In the practice, Cisco switches enable Rsdp point-to-point edge ports by enabling port fast on those ports. Cool. All right. BPDU guard. All right. I believe this is going to be the last topic that we're going to be discussing in this chapter before we move on to Cisco packet tracer here very shortly. Okay, guys. So STP and Rsdp open up a LAN, a local area network, to several different types of possible security exposures. All right. Any attacker could connect to a switch to one of these ports with a low STP Rsdp priority value and become root switch. All right. The new Stp Rstp topology could have worse performance than the desired topology. The attacker could plug into multiple ports, into multiple switches, becoming root, and actually forward much of the traffic in the LAN without the network staff realizing. The attacker could use the LAN to analyze and copy large amounts of data sent throughout that LAN. Users could incorrectly harm the LAN when they buy and connect an inexpensive consumer LAN switch, one that does not use STP or Rsdp. Such switches without STP functions would not choose to block. So, what PDU guard is doing, it's preventing. So, in your Cisco switch with BPDU guard, it's preventing attacks. All right, it's preventing you as a consumer from, say you bought Joe Schmo's switch from who knows who, and that switch, yeah, it might be advertised as being a great switch and all, but it might not have STP enabled in it. It might not have Rsdp, all right, enabled in it. You plug that switch now into your beautiful network, all right, without PPDU, you're going to create a broadcast storm now. And you might not even know what's going on, all right? You plug that Sally Daisel switch into your whole network, and boom goes your network, all right? PBDU guard, all right? The Cisco PBDU guard features help defeat these kinds of problems by disabling a port if any PBDUs are receiving on that. Let me read that again. The Cisco PBDU guard features helps defeat these kinds of problems by disabling a port if any PBDUs are received on the port. So this feature is particularly useful on ports that should be used only as an access port, all right, access port, or neither connected to any other switches. In addition, PBDU guard features helps prevent problems with port fast. Port fast should be enabled only on access ports that connect to user devices, not to other local area switches, not to switches. Using PBDU guard on these same ports makes sense because if any other switches connect to those such ports, the local switch can disable the ports before the loop occurs. So, PBDU guard you would enable on interfaces that are going to end devices, any interfaces that are not part of your your beautiful Ethernet channeled redundant beautiful topology. You would enable PBDU guard on all the other interfaces on your switches, or on the other interfaces on the switches, not the interfaces that are part of your Stp, Rsdp, Ethernet channel awesomeness. You would enable PBDU guard on all those other interfaces because to prevent, again, Joe Schmoes has a great idea to start hooking up his Sally McDonald switch to your network here and creating a whole heap of problems for yourself, or an attacker hooking up and then figuring out to create himself as being the root switch by assigning a lower priority. All right, you don't want all of that to happen. So that's what PBDU guard is enabling. Okay. All right, we did it. Woo! All right, we've gotten down to the chapter review. We're just going to touch some key topics. List the 3 main problems that occur when not using STP in a local area network with redundant links. List the reasons why a switch chooses to place an interface into forwarding or blocking state. List the most important fields in the hello BPDU messages. List logic of the switch elections. The root switch elections. Show how interfaces calculate their root cost. List the original and current default STP port cost for various interface speeds. Summary description of steady state STP operations, STP timers. Definitions of what occurs in the listening and learning state. Summary of the 802.1 delta state. Key similarities between the 802.1 delta STP and the 802.1 whiskey Rsdp. Methods Rsdp uses to reduce convergence time. List of the 802.1 whiskey port roles. Comparisons of port states with the 802.1 delta and the 802.1 whiskey. Key terms. All right, let's go over some key terms. We have blocking state, PBDU guard, bridge ID, bridge protocol data unit. That's a tough one. It flows off my tongue so awfully. BPDU, bridge protocol data unit. Let's say it one more time. Bridge protocol data unit. All right. Designated ports, Ethernet channel, forward delay, forwarding state. Hello BPDUs, learning state, listening state, max age, port fast, root port, root switch, root bus, spanning tree protocol, STP, rapid STP. All right. Alternate ports, backup ports, disabled ports, discarding state. Woo! What up, purple neon? Woo! All right. I think we were very, very successful here. I am so happy right now. All right. What we're going to do now is we're going to head over to Cisco Packet Tracer. We're going to create ourselves a topology. We're going to go through, we're going to look at some of the messages that flow through our network. All right. And we'll take a look at some of these hello PPDUs. And well, yeah. So we're just going to go from there. So let me switch my cameras over real quick, everybody. Hello. All right. Yeah, I'm just gonna switch over. Again, just gotta log back into my server real quick so I can get back to my Windows computer I got running. All right. Now we are here. All right. So we're over here in Cisco Packet Tracer. And yeah, if this is the first time joining me, I got a VM, I got a Windows VM running in the background that I run Cisco Packet Tracer off of. Just in case Cisco Packet Tracer decides to crash on me, it's not gonna tear down our stream today. So that's why I got it running in the background off of my EXXI server. So yeah, let's come over here. And we're just going to grab a couple switches. And we're going to set up the same similar topology as you saw as we were going through our chapter review. All right. We're going to set up our links. And we're going to take a look. Let me edit the filter. We don't need this. So much. All right, that's fine. La-da-dee, la-da-da-da-da-da, la-da-da-dee. And let's just press go. So you can always see what Stp is already doing. So Stp, and we'll take a look at these. This is when, again, I haven't configured anything yet. So this is spanning tree protocol already sending out these hello PPDU messages, because right now it's trying to figure out who's gonna be root. All right. Once it figures out who's gonna be root, it's then gonna be trying to figure out, okay, well then we gotta come up with some We got to figure out cost and we'll stop. Let's stop. I want to look at these packets. Let's look at this one. Oh, it's still going, isn't it? All right, you can do your thing. All right. So there's a hello time. Obviously, we still have the default set at 2 seconds. All right. Max age, 20 seconds. All right. The port ID. Now this came from, let's take a look. Stop. I said stop. You crazy thing. Stay there. Oh, it's still going through its whole convergence. You know what? I'm going to reset this all. Let's reset this. Reset simulation. Add a little bit. All right. So what do we got? Here's our port ID, 32769. Let's write that down. And this is coming from switch 0, so we're going to say switch 0. Say 0, just to keep things simple. Its ID is 32769. All right, this is from switch 0 to switch 2. What are you stating? So here again, so here's that root ID. All right, so 7269, 7269. Bridge ID is that bridge ID 7269. It's given out, and then that's its MAC address. So that's the MAC address that it's coming from, the 003s. And that will be, see that. Again, there's the port ID. You got to show up. Still doing its convergence. You'll see all these links are starting to come up now. And then we'll see in a second when it's all stopped. You might have actually done it, and it probably put, I'm guessing it probably put this one in its blocking state. Not pausing anymore. Crazy Cisco packet tracer losing its marbles on me. All right. Back up. All right. So we'll take a look at this one now. So they're all stating the same one. So we're gonna have to go with MAC addresses. So let's write down some of these MAC addresses. I need to stop you, but you're getting too crazy for me. Getting crazy on me. You're losing it. Let's look at some of these MAC addresses. So we're on switch 1. So switch 1 off of the 501. So the 501 is saying that the MAC address for switch 2 over here is this. It's already learned all this cool stuff. Cool. All right. So what are we saying? So we're saying switch 2. It's 501. It is going to the 0. That's A 00 alpha .417 delta 0.07. And then off of its far02, it states this. That's switch 3, so that's switch 1, as it states in topology, 0.0 delta 746 3401. Far 01. Switch 0, switch 0, 0.0 delta 0. B A 1 2101. Those MAC addresses. Off its far 02. Switch 31 again. 0. Other MAC is 0.0. Yep, 0.0. Alpha 4.7. 7 delta 0.72, and then off of the other one, the far 01 states that one switch 2, it is 0.0 delta BA. BA 912102. Cool. All right. So that's that. We have some MAC addresses. Now we're gonna look. We're gonna be able to see. We're gonna be able to see with some show commands. What switch became root. I don't want that to happen. And then what ports and all that are in the blocking phase now. Yeah. So let's look at some cost here. All right. All right. So here we go. So root ID is going to be this address. So what do we got? So 21 00 rich port ID 0 states that the root ID is that 003 dot E 4 2 echo 18 is the root bridge. Okay, so that's the root bridge. So F01, they're both in the designated forwarding state. Here. All right. So S1 is root. S1 became root. All right. S1 became root. On S, so I should have renamed them all, but so S0 is root. S1 is stating that it's fuzz01. Let's just go back up here, so stop being goofy. So it's fuzz01 that's going to switch 0 over here. That's going to be its RP, its root port. So root port, and then it's fuzz02. That's its designated port. Okay. Let's look at this one. All right. And obviously Rsdp is working because we have root and alternate now. So what happened is fuzz01 became root, and then fuzz02 is now alternate, which is in the if we're thinking STP, which is in the blocking. All right. So all the hello messages and all that worked, figured out that its ports, these ports on all of its switches here. Hold on, let me get back to switch 1. Switch 0. I keep calling it switch 1. Stop calling it switch 1. All right, so these are the designated ports. Designated ports. All right, and it figured that all out because of the cost. So the address on switch 0 was lower than the address on switch 0 on switch 1 over here. I gotta stop doing that. All right. And there. And was the lowest, had the lowest BI bridge ID out of this whole topology here. And then obviously, then it made the decision to then say, okay, since this is root now, I have to then choose out of which ports I'm going to be my roots, which is going to be the lowest cost to the root switch. And then we have a designated port, and then Rsdp assigns an alternate port on. So if, say, we had a failure on this, so if we were to come over here, and delete this now. And let's draw up a simulation again. And then that port just came up, so we'll run show spanning tree again. The fuzz01 now has come into, now it's the root. It came up now because it was alternate, and now it becomes the root port now. Obviously, it still states as switch 0 still root. All right, this bridge is root. All right, and it's, obviously it still only has that. Now it only has one port because one failed. So that is pretty much the basics of span and tree protocol. Now, can I create a broadcast storm inside Cisco Packet Tracer? See if I can. I guess if I turn, can I turn Stp off? Let me do that. I'm curious to see if I can turn the Stp off. Still sending Stp messages, but I wasn't able to turn it off. Let me clear this board real quick. Make a new board. This time I'll give everything a better name, huh? Guess we can go into, let's make some Ethernet channels here. So we'll do. All right. Bigger. Let's get bigger. You know. All right. So what do we got? So we have 501 and 502. All right. Let's go interface 50 configuration. All right, so we're in there. I'm gonna say channel. Channel group. Channel group mode on. Oh, I see what I can do that. Put it because one of the links just got put down. I see. Because of that. Hold on. Erase all these links then. Switch. New switch. Okay, let's do this guy. Configuration terminal mode. And we're gonna move into the interface range mode. 5.0.1, 2. Alright, next channel. It's not gonna let me do this, is it? Oh, okay, I guess. I see what I'm going. So interface port channel. Port channel. I'm gonna say 1, 2. So additional parameters. All right, now let's move into the I see. I see. So, okay. So let's exit. Interface, range, 501 through 2. Then it's the channel. There it goes. Alright, so that sets up that one. Now exit. Now I have to make another interface. Port channel 2. Exit. And then we're going to do the interface range. 0, 3, 3 to 4. Range. 3 to 4. Channel. Channel. Group. Mode. 2. Mode on. Alright, beautiful. So then, let's come over here. We're going to do the same things. So interface, port channel 1, interface, range, 1 to 2, mode 1, exit, 2, interface, range, 5, 3, 4 now, 2, mode 1. Interface, port 1, interface, range 5, 0, 1 to 2, channel, group 1, on, exit, interface, port, channel 2, interface, range 5, 0, 3 to 4, channel, group 2, hold on. Now we can create our wiki links. 501, 2501, 2, 2502, One. Oh, you know what I gotta do? Yeah. I gotta connect that to port 2 now. Right. Three. This one. That puts those 2 port groups up. Puts those 2 port groups up. Now, yeah. I gotta create a whole new range, so let me exit out of there. Port channel, I'm gonna say 3. Interface, port channel 3. Interface, interface, range, 0. Say 5, 6. Channel, group 3. Mode on. Yeah. Exit. Interface. Port. Channel 3. Interface. Range. 0. Say 5. Six. Group 3. Right. That should done. My bad. All right. Now it's going to be freaking out for a little bit. Gets everything set up. So it is stating, cool, look at that. All right. So now that we have an Ethernet channel up, it took that bundled channel. Remember, when we make an Ethernet channel, it's taking physical links and bundling them together. Okay. So we got port channel 3. So it looks like this switch right here became the root switch. Let's exit. Sorry for all that sloppiness, guys. In the beginning. So let's look at it now. Spanning tree. All right. So this is the root bridge now. So that one became root. All right. And the designated ports, it's using the port. So port channel 2 and port channel 3. All right. Those are those Ethernet ports we just created. Those are those. Remember, it's using those like it's using those as single links, but logically it's looking at those multiple links as single links. Okay. And then let's go over here. Let's run. Let's exit and let's do a show 3 again. All right. Cool. And that. So our port channel 2 is root. All right. So this is its root. All right. And then port channel 1 is alternate. Okay. Cool. So that's a look on how to set up port channels, and then how Rsdp Rapid Spanning Tree Protocol it still uses that same logic on those port groups. Now again, if we were to have a failure, so let's come over here and let's delete one of these links. All right, let's come back over here. Now it didn't change. All right, so it's still using the same port groups as it did before. All right, so port group 3 is still root. All right, still root. This is root right here. Port 01 is designated, so it's going right here. All right, same thing over here. All right, it didn't change any of its logic. All right, just because we had a failure on one of our links, it still is using that port group as it would in actual interface. Okay, so that's the use of bundling multiple links into an Ethernet channel. Okay. Cool. That was fun. That was actually wicked fun. So creates a channel group 1 as an Ethernet channel and assigns interface as part of it. I'm looking at multiple configurations now to do this. Yeah, so that's just a look at so that's a look at Stp. All right. That's a quick look at Ethernet channels, how to configure Ethernet channels, and then getting some of the show commands to show what's going on with that. Taking a look at the hello messages, how spanning tree and rapid spanning tree, how it's choosing root bridges, so root bridges, how it's choosing root ports, so you got root port, how it's then turning blocking ports, turning ports into alternate ports, you know, all in so it doesn't create a broadcast storm. All right, so when we add redundant links to our topology, we don't start sending frames throughout the entire over and over, broadcasting those frames throughout our network. So yeah, this has been a fun little lab, honestly. This is actually the first time I think this is like the first time I think I started messing with Ethernet channels and rapid spanning tree protocol and rapid spanning tree and whatnot. Well, I'm gonna have to spend some time on. I'm definitely gonna spend some more time on grouping together Ethernet channels and port groups and whatnot, because that was pretty neat. Again, guys, I'm still, I'm learning this along with you guys. So, again, I kind of fumbled it in the beginning, but we got it together. We created those links. And yeah, and let's just get that link back up again. So what do we got? 506 and then 506, and then that should come up again. And we should pick back up on our groups once it's done doing its it's going through its convergence right now, isn't it? Yeah, look at that. It's even showing the states forwarding. It's in learning. So it's actually showing you what the state it's in. So the state, okay, learning. It's even, here's the cost. So each of these has a cost, okay. And then here, let's run it again. And now you can see now that it's moved into the forwarding. Okay, so you saw it when it was in the learning, all right. And now you see it, it's in the forwarding. All right. Cool. That is neato. Yeah, so here's the cost of 9. And that's when it was showing this was the cost of showing the cost of 9 too. Let's take a look at this one. Oh, so there's our bridge IDs right there. So what's that? Charlie 38801. All right, so next time I know to look at it like this. Cool. That was fun. All right. Yeah, guys. I want to thank you. We've got a couple followers tonight. Thank you, Purple, and thank you, Crispy, for your follows tonight. Thank you, everybody out there, for hanging out with me tonight as we went through Stp, spanning tree protocol, and Rsdp. We set up a quick and easy topology. We looked at how Stp and Rsdp is, how it does its convergence, and it designates root ports, root bridges, designated ports, and also alternate ports, Rsdp alternate ports. If these switches were running Stp, they would be putting those ports into the blocking. Okay. Yeah. If there's no other questions out there, guys, I want to thank you all for joining me tonight. Again, tomorrow we're going to continue on our journey. We're going to continue on our journey into. We're going to be continuing on to our journey to Rsdp and Ethernet channel configuration. So, even though we did that, we labbed that up tonight, we're going to be diving deeper into it tomorrow. And tomorrow I guess I'll have a better, once we review this chapter, I'll have a better idea on how to set this topology up better. Because I think tomorrow, when we review chapter 10 here, let's just take a quick review. Understand Stp, the need for Stp. All right, so tomorrow it's actually getting into the configuration of what we we went through here tonight. So that's going to be showing us the span and tree mode. It's actually going to be getting into the okay, so we have, it's actually going to be showing us the command line. It's going to be showing us how to do this off the command line here with multiple VLANs. Okay. All right. Yeah, so I hope you guys can join us tomorrow. Join me tomorrow. Tomorrow it gets into the actual configurations of what we were mocking up here in Cisco Packet Tracer here. And gets into multiple channels and how that works. Load balancing, so it touches on some topics of load balancing as well. So I believe, so tomorrow again, tomorrow will be Rsdp and Ethernet channel configuration. So it'll be the actual configurations of this on how to do it correctly. Again, that's kind of why I probably stumbled a little bit in the beginning of it, just because I haven't reviewed chapter 10 yet. So join us tomorrow again, 5 o'clock p.m. Eastern Standard Time. Back on the same channel again. We'll be doing chapter 10 review. From there, Thursday will be the big review day. That's when we'll do a big review of part 1, part 2, and now part 3. Okay, so Thursday will be a big review day of everything. Friday will be our lab day. All right, so Friday would be lab day for us to keep going over command line configurations like we did tonight. That way we hammer down our command line, our actual configurations on these devices. Instead of just continuing to talk about them, I need some more hands-on, as you guys can obviously tell already. When it comes to this type of configurations, I definitely need more practice to be more fluent. There's one thing to just do it. It's another thing to be fluent in understanding how to just blast through these configurations. You know what I'm saying? That's where I want to be. I want to be able to, from start to finish, I want to know, once I'm on that command line, I want to know exactly all the commands I need to get to so I can set up, Ethernet channels, load balance, and, get all my show commands correct. So that's why Friday, I think we need to spend a lot of time labbing things up, multiple types of labs. We'll go from, we'll go from part 1 all the way to where we're at now, with multiple different types of labs. And again, hopefully, if you guys are interested, download Cisco Packet Tracer. If you guys have questions for me tomorrow on how to download Cisco Packet Tracer, tomorrow will be the day for those types of, Thursday will be the day for those types of questions. That way, Friday, we're already set up for our lab day. Okay, so remember, tomorrow we'll be reviewing chapter 10. That's Rsdp Ethernet channel configuration. So kind of like what we touched on right now. Thursday will be the review of part 1, part 2, and part 3 now. All right, that'll be a lot of time going through the practice exam over and over and over and over again until we really get that textbook knowledge slam dunked into our brains. We'll do a quick review of everything, and then what I want to see happen is, if anybody again is interested out there, let's walk through the steps to get Cisco Packet Tracer downloaded, so that way come Friday we can spend the time we're going to need to just lab it out. It'd be this right here, guys, and just labbing it, everything that we've learned so far. That way we can really be command line heroes. So if there's no questions out there, I want to thank everybody for joining me tonight, and I wish you guys a safe and lovely night. Again, from my house to yours, I love every single one of you guys. Thank you very much. Mwah! Have a good night, everybody.